Hello everyone, just give me a few minutes so I can set up things. We'll begin in a few minutes. Hi Eagle, hi Thomas. Thanks for joining the stream. Hi everyone for joining the stream. Yeah, so today we're gonna be talking about stochastic differential equations, and it's gonna be a very exciting time together. And so right now I'm trying to reboot the now somewhat dormant stochastic calculus video series. Last week we did 2 episodes about stochastic processes in physics, and this is going to be very relevant to today's topic as well. So, this is my first live stream here. Was just finishing up one of the measure series ones. Pretty exciting stuff. Oh, thank you very much for tuning into the measure series one. Yeah, we'll be continuing on that one. It's going to be very much a so to say a very thorough, in my opinion. And anyway, so coming back to stochastic differential equation, though, we won't be talking much about measure theory, just to maximize accessibility. The measure theory series isn't supposed to be a prerequisite for this one. That's more for literacy, I suppose, because measure theory is really the, so to say, the lingua franca, the standard language in advanced probability and stochastic process. Without measure theory, you really have to rely on somebody else to translate the material for you. You don't have and you will have very little without it. Okay, without it, you will have very little independent ability to research, to study. So that's mainly a language thing. So we don't strive for like proving new theorems in measure theory or anything like that. Just like the basic literacy to understand measure theoretic probability and relevant literature. Yeah, as you guys hear cats. Yeah, I'm doing fine. I'm doing very well actually. Thank you very much, Ego. So because this is our first stream on the topic, we will look at the literature. So I put a few links in the description, as usual. As I mentioned earlier in the integral transform stream, it's like whenever I start a new topic, I want to make that video, or sorry, I want to make that live stream or video also a a a list or a place to compile book and resource recommendations. Like, of course, that will include textbooks, papers, and also videos, lectures, courses. Sometimes universities put their courses completely open, which is a godsend. So those are included as well. So I put 4 books which I find useful in the description, and we will be using 2 of them for this series. So let's get into the first one. So this one right here, called an Introduction to Numerical Simulation of Stochastic Differential Equations. This is perhaps, in my opinion, the most accessible book on SDEs on the market. Okay, stochastic differential equation has a formidable reputation. This is typically a graduate level topic. It is a PhD level topic, if not master's. Okay, so a serious study of stochastic differential equations has so many prerequisites that it is, in my opinion, perhaps prohibitive to non-math majors, but we're aiming for a general STEM background. Okay, it's not just for math majors. Okay, awesome. Thanks. That's great to hear as well, Ego. Glad you're doing great. So yeah, this one is very extremely approachable. It only assumes basic probability, and it has a nice review for that as well, for the kind of probability that you need for this book, and some background about the basics of differential equations, like non-stochastic deterministic differential equation. Ordinary differential equation is fine. If you know some PDE, that's better. Yeah, Cat. You can probably hear Cat in the background. Hi, Steve, for joining the stream. Great to see you here, as always. So, yeah, this one is an undergraduate level book and is very accessible. And it would be helpful if you also have some knowledge about numerical solutions of OD as well, but that's not super essential. So it's the essentials for this essential prerequisite for this book is basic probability at the level of just introductory level probability, a first course in probability that covers things like the normal distribution, mean and variance is enough, as well as basics of differential equations. So for example, how do you do separation of variables? How do you model a phenomenon using differential equation? Yeah, Cat seems to be very interested in the math. Well, they say, what did they say? Apple is not too far from the tree, huh? Okay, I just woke up, so my voice might sound a little bit weak. Okay, I'll try to gain more energy. So yeah, the reason we mentioned this book is because numerical simulation is usually how SDEs are solved in practice. You probably know that in practice, ordinary differential equations are rarely solved by analytic solutions, and this is also perhaps it's definitely more true when it comes to SDEs, category theory. So here, and actually, next week or perhaps week after next week, I have not yet completely decided, is that we're going to look at the mathematics of diffusion models. So have you guys heard of the diffusion models? Okay, this is Chinese. Diffusion model is a kind of deep generative model, and nowadays it's very much a hot topic, and its mathematical foundation is heavily dependent on diffusion modeled by stochastic differential equations. I'm not sure whether next week we can do that, but definitely before the 29th. Okay, we'll do a live for diffusion models. So just take a brief look of what kind of math is needed, okay, for diffusion models, and you will see why SD is of critical importance. Okay, so these are some conditional distributions. Actually, I have to be completely honest, I don't know exactly how this works. I think I have the probabilistic background and ingredients for this subject, but I still haven't yet figured out how it works. So if we do a live, it's going to be me trying to figure out stuff, okay? And hopefully we will learn something together. So these are, you can see some of the crazy math here. This is a so-called Langevin equation. This is an example of a stochastic differential equation, which can then be equivalently described by the Fokker-Planck equation. For Fokker-Planck equation is a PDE, it's not a SDE. The Fokker-Planck equation will be derived next week in our stochastic process for physicists series. Okay, well, next week we will actually derive this. So by the time we reach the diffusion model, when we have the diffusion model stream, we will already have an overlook of SD as well as Fokker-Planck. So to make our lives a bit easier. Yeah, so the mass needed is quite formidable. This is another SDE as well. Continuous diffusion process. You see stochastic differential equation seems to be popping up everywhere. I saw at least 4 SDEs already. Okay, even though I don't know whether how they stitch together to form the diffusion model. And this is the Fokker-Planck equation. This is the PDE. So the interplay between PDE and SDE is going to be a major theme in our stochastic calculus series. Yeah, so the more SDE. This is another SDE. So everything seems to be related to SDE, another SDE. And this is done by SDE integration methods such as Euler-Maruyama method. This is the numerical method in SDE, which is covered in this book. So as you can see, this is the gold mine for beginners of SDE, as well as simulation of SDE. And it's not just for beginners, it has advanced methods as well. Okay, so this book is very approachable. The two authors, Desmond Hayam and Peter Kloiden, they are top tier numerical analysts. Desmond Hayam, British mathematician. He has a Google Scholar page. You see, this is Desmond Hayam. Very well. Actually, you know what, guys? I forgot to include this paper. Damn. How could I forgot this? My goodness. This paper, man. I will link this I'll put the link here in the chat. This paper, man, is so nice. It's his top-sided paper. And the flavor of this paper is very much the same as this book. If you read this paper, you will know what this book is like. This book is an expansion of this paper, which is fantastic. Okay. It is so approachable. I don't know how else I can put it. Okay, this is so approachable. Actually, you know what? I think I'm gonna follow this one now. Okay, I prepared a bunch of my notes, and I forgot about this note. And I forgot about this paper. How clueless I was. I will just go over this paper. Okay, makes my life actually a whole lot easier. I was worrying about, okay, what should I do today? All right, we'll cover this paper actually. My goodness, how could I forget about this one? Okay, so that's the first resource listed in the description, and I'll also put this paper in the description later. Okay, and here the second resource is this one. It's called Applied Stochastic Differential Equation, Applied SDE. What's going on? Why there's no image here? Yeah, this one is also a great resource for applied researchers. So if you're doing a lot of modelings with stochastic differential equations for physics, for finance, for engineering, well, and also nowadays for generative AI, go check out this one. No measure theory needed. Just take a look at the topic. You need some background in ODE, pragmatic introduction to SDE, Ito calculus and SDE, probability distribution and statistics of SDE, statistics of linear SDE, useful theorem and formulas, numerical simulation, approximation of nonlinear SDEs, filtering and smoothing theory. Excellent topic selection, in my opinion. Oh, there's more. Parametric estimation in SDE. Oh, so SDE in machine learning. Oh, go check out this one. See, no measure theory for this one either. Applied stochastic differential equation. Oops, sorry, my bad. Yeah, this one written by two Finnish mathematicians. So go ahead and check out this one. And of course, we have the standard reference. This is a standard grad textbook on SDE. called Stochastic Differential Equation with Introduction with Application, written by Øksendal. Is that how do you pronounce it? He's Norwegian. This is a standard grad text, as I mentioned, used in the statistics department as well as in quant department, financial mathematics department. Okay, and it is based on measure theory, although, let's just put it this way, it is not heavy on the formalism. If you are extremely motivated beginner with a good background in calculus-based probability, you can still follow the formulas and treat the measure theory as black boxes and follow this book. So Øksendal, although he presented the material in a mathematically rigorous fashion with full proofs and all that, he still greatly emphasizes intuitions. So this is also, I would recommend this to even people without a measure theory background. Okay, this is the gold standard in SDE. Okay, and last but not least, there's the shorter book by Evans, L.C. Evans. So L.C. Evans, if you're in the applied community, you probably heard of L.C. Evans. He wrote the book on PDE. L.C. Evans, professor at, I believe, UC Berkeley. Yeah, UC Berkeley. So he wrote a short set of notes. It used to be free, and now he published it. So now there's no free version, at least like legal free version of it. It used to be a set of lecture notes he had at UCLA. And this book, okay, so now you can use the link, fine. So this book is rather short. It's barely under 200 pages, which is short considering the barrier of entry and the depth of the subject, such as SDE, like the SDE. So it's really concise. And he's first and foremost a control theorist. So his introduction is more geared towards stochastic control theory, which is great if that's your objective. Okay, so SDE is used in so many different fields, and as an applied math channel, we try to accommodate audience with those diverse goals. Okay, we never really just do math for its own sake. Always have a target background, target audience, so to say. SDE is used in physics. Well, it came from physics. It came from the study of Brownian motion, which we covered on the Thursday stream of the work by Langevin, Øksendal, and Uhlenbeck. That's the origin of SDE. SDE came from physics. Pretty much all good mathematics came from physics. Wow. And now, next you have the finance, obviously. Right. Stochastic differential equations are used to model interest rates, stock prices, and then and those models are used for portfolio optimizations as well as option pricing, the pricing of financial instruments. Okay, and also where else? In engineering, for example, like what we saw here, filtering and smoothing. The celebrated Kalman filter in continuous time is modeled by SDE, filtering and smoothing theory, the famous Kalman filter, as well as control, stochastic control. So we saw a introduction to optimal control a few weeks earlier, but that was deterministic control. Like, what if your system has some noise in it? Then suddenly the dynamic is modeled by SDE as opposed to an ODE. So to control a stochastic system, of course, you need SDE. So it's kind of self-explanatory. SDE really is everywhere in applied math, in applied sciences, engineering. It's a great shame that this is such a fundamental subject and the barrier of entry is so high. Okay, so today we're gonna remedy that situation perhaps a little bit. Okay, or I'm going to follow Professor Hayam's paper to make things a little bit manageable. Okay, so let me just catch up on chat to see if there's anything, any questions asked. Can you elaborate differences between stochastic DF and just what is stochastic DF? You mean DE? I'm not sure what DF is. So differential equation is an equation that involves an unknown function and its derivative, like the Newton's law. F equals ma is a differential equation because acceleration is a derivative of the position, and typically the force depends on the position as well. And stochastic DE, as we will see in the paper, is an ordinary differential equation with noise. So now let's suppose you have some force that is random or has great fluctuations, and the exact modeling is very difficult, so you use a random term in the differential equation. And now, because of the random term, the solution of the differential equation is a random process as opposed to a deterministic function. Okay, so yeah, or control theory. Yeah, control theory. Yes, you need to check it out. I'll show you the example I was talking about, also by L.C. Evans. So if you're interested in applied mathematics, PDEs, ODEs, control theory, you definitely need to check out L.C. Evans's work. So Evans, let me just search it in my set of notes. Yeah, we did a live on optimal control written by Evans. That's the course notes by Evans. We walked through most of the examples in chapter 1, but as you can see, chapter 7 is introduction to stochastic control. And for stochastic control, you absolutely need SDE, or at least stochastic control in continuous time, because there's also discrete stochastic control theory, which requires much less background, right? So we might take a look at stochastic control theory in a discrete setting as well, because that's a much more approachable subject. Stochastic control in continuous time, well, you need a lot of background for that. Optimal control and SDE, both are quite formidable. So for example, this is chapter 7. Just extremely fascinating stuff. So here, introduction, motivation, review of probability, Brownian motion. We'll be talking about this. Although we already have videos on Brownian motions, we'll cover it like from the start. This way the stream is self-contained. I'm not going to assume that you already watched the stochastic video so far. Okay, 7.3 SDE, stochastic calculus, Ito's chain rule, dynamic programming, application, optimal portfolio selection. You see, application in finance. You absolutely need SDE. For example, this is SDE. This is ODE, x dot equals f of xt. SDE is the same right-hand side, but now with a noise term. This is called a white noise, causing random fluctuation. And this complicates things a lot. Okay. For example, now x can be a nowhere differentiable function, but still you need to make sense out of the derivative. Okay. So this comes from physics, and now it's everywhere. Okay. Anyway, this is L.C. Evans's notes on optimal control. So go ahead and download this one. And this is a free paper. Yeah, free paper by Desmond Hayam. You see, a practical and accessible introduction to numerical methods for SDE is given. Reader is assumed to be familiar with Euler's method for deterministic differential equation. And we'll do a review for that as well, this first year calculus. Or at least have an intuitive feel for the concept of a random variable. And to have at least intuitive feel
for the concept of random variable, which I assume everyone in the stream already have. However, no knowledge of advanced probability theory or stochastic process is assumed, which is awesome. The article is built around 10 MATLAB programs. There won't be any live coding on this slide. We'll be mostly just doing the fundamental math. And the topics covers including stochastic integration, Euler-Maruyama method. Yeah, Euler-Maruyama method is the stochastic version of the Euler's method for ODE. Okay. And this is used as we already seen, this method is used in diffusion models for AI. Here, just to briefly remind ourselves, this is a diffusion model. Yeah, Euler-Maruyama method. Okay, so if you know this, then you have the ingredients to build diffusion model. Okay, and actually, let me just show you this one. I was kindly informed of this resource from MIT OCW, or actually just MIT. I think also MIT OCW, they have their the lectures. Yeah, this is MIT OCW, a series of lectures on diffusion model. And for example, if you just go to slides 1, okay, and as you can see, SDE is the foundation, ODE sampling, SDE sampling, and whatnot. Okay, this is Øksendal process, which we covered last week in our stochastic process for physicists series. Okay, so it's like an exponential decay function. See, it looks like exponential decay. This is a deterministic exponential decay model, and now it just added with noise. As sigma gets bigger, the noise level increase. So this is a clear example of a classic ODE turning into an SDE. Okay, Øksendal process. Okay, Euler-Maruyama method, it's in here. Okay, so I'll share this in the chat as well for diffusion model. Okay, no later than the end of this month, we will be taking a look at this particular resource. Hopefully we can figure out diffusion models together. Okay, I'm pretty sure, I'm not even going to ask you whether you're interested in, I'm pretty damn sure you're interested in. Okay, it will be easier to notice who isn't. It will be easier to ask who isn't interested in this stuff. Okay, this is diffusion model. And speaking of which, there's a new book-length treatment of diffusion model. Diffusion model. And it has like Python notebooks as well. The full solution is available. So yeah, if you like, so this is quite literally a godsend. Solutions can be found here. Okay, so yeah, we have plenty of stuff to figure out. What else am I trying to say? Yeah, so we were reading about this one. Actually, you know what, guys? Why don't we spend some time trying to read slides 1? Just after we get to know the basics of Brownian motion, and perhaps even right now. I don't see why. If you don't understand something, if we don't understand something, now we have a concrete objective. How about that? Okay, so right now I'm just going to finish the abstract by Haiyan. Euler-Maruyama method, Milstein's method, strong and weak convergence. So these are notions in numerical analysis. Linear stability also in numerical analysis, and stochastic chain rule. That's the Ito's rule, Ito's lemma, stochastic chain rule, which we already covered in a video. I don't know if we will have time to do Ito's chain rule today, or stochastic chain rule, Ito's formula, Ito's Doibelin formula today, but we will see. Okay, the main objective today is to give an overview, the fundamental definitions, and not proving theorems. Okay. Okay. So I was talking about a book length treatment of SDE. No, not SDE, but diffusion model. The principles of diffusion model. This one. It's on archive because right now it's a draft. Be sure to grab it sooner rather than later, because once it's published, it's no longer for free. Okay. Yeah. So this is a book length treatment, and it's like 400 pages or something. Looks promising. Okay. Book length treatment. What's up with chat? Why I cannot type? English, please. Book length treatment of diffusion model. Okay, so there's that. Go check this out. I'll be completely honest, I don't have background in deep generative modeling, but I think once again, I think I have the necessary background for the stochastic process, for diffusion stuff, Fokker-Planck, that kind of thing. So I'll have to see how well I'll do when it comes to understanding the diffusion process. Okay, and that's our objective. I mean, it's not going to be a single-minded mission to purely understand diffusion models. Okay, so we're still going to, in the process, look at classical applications of SDE in physics, finance, and engineering. Okay. Sorry guys, my voice is screwed up this morning. Okay, let me catch up with chat. So chat says, I first encountered SDE in sampling from probability distribution, where we use the Langerman sampler. Oh great, awesome, indeed. Yeah, control theory is pretty useful in engineering. What's the book again? Oh, the book, yeah, sorry, Ego. It's this one, L.C. Evans website. L.C. Evans, this one. It's Introduction to Mathematical Optimal Control Theory. Okay, this one. So yeah, and in particular, chapter 7, Introduction to Stochastic Control. I'm pretty sure there are dedicated books on stochastic control, but this is just one chapter and it's pretty manageable. Well, still, it's not an easy read. Okay, I do not promise easy read on this channel like ever, but you know the drill. So because we're dealing with intrinsically a difficult subject, but we're trying to show there is a pathway to it. And where's Chad? Yeah, it's here. This is L.C. Evans. Notes on optimal control. See chapter 7 for stochastic control. All right. Why is my live stream 24 minutes late? I'm not sure. Okay. Can I ask for application example? So you mean you want this featured stochastic portfolio theory? Do you want to see this as a like feature on the channel, like we do a live or video of this topic? Is that what you asked for? What it means? Oh, that's a book, huh? Constructing stored portfolio. Okay. Um, I don't see why not. It feels fitting with the main theme of the channel, but it's gonna take a while for us to get there. That's the bad news. That's the bad news. Okay, and because we're mostly doing a topic that, so to say, towards a general STEM audience, we'll see how manageable this is for, say, uh, because at a certain point you cannot avoid measure theory anymore. We'll see how well that do. Okay, but pretty much this is a more specialized application, right? This is a more specialized application. It's um, we still haven't even done Black-Scholes yet. Right? At least we need to do Black-Scholes first, guys. Vote in chat. I mean, not vote, but can I put a vote in chat, guys? I don't even know. I'm such a newbie when it comes to streaming. Which one do you guys want to see first, Black-Scholes or diffusion model? Say something in chat, please. Which application of SDE would you like to see first? Black-Scholes or Black-Scholes, which includes SDE and PDE and formula, the solution of the PDE basically, or diffusion model? Question mark? Okay, go ahead and think about it. Okay, of course they will both be covered, but just which one you want to see first. Okay, so in the meantime, we'll just get started with the actual material. Either way, it's not really my area. Okay, cool. Okay, that's fine then. I'll take that as indifference, or at least as far as Steve is concerned. Okay, let's get started. SDE models plays a prominent role in a range of application areas, including biology, chemistry, epidemiology, mechanics, microelectronics, economics, and finance. Well, is there anything that is not dependent on SDE? I don't know. Probably none. Okay. +1 for diffusion model. Okay, everyone wants to jump on the bandwagon. So am I. So do I. Okay, so let's go. And diffusion model first. Okay. Just kidding. Okay. So, a complete understanding of SDE theory requires familiarity with advanced probability and stochastic process. That's true. Picking up this material is likely to be daunting for a typical applied mathematics student. However, it is possible to appreciate the basics of how to simulate SDE numerically with just a background knowledge of Euler's method for deterministic ODE and an intuitive understanding of random variables. Furthermore, experience with the numerical methods give a useful first step towards the underlying theory of SDEs. Hence, in this article, we explain how to apply simple numerical methods to an SDE, and discuss concepts such as convergence and linear stability from a practical viewpoint. Our main target audience comprises of advanced undergraduate and beginning graduate students. Actually, this is my target audience too. Same target audience. Advanced undergraduate and beginning grads. That's the target audience of this channel. Okay. And by advanced undergrad, I don't mean advanced undergraduate math student. Okay. It is aimed for general STEM audience, like people who, let's say, coming from other backgrounds of STEM, computer science, engineering, physics, chemistry, or even social science, counts as well, economics, finance, but unnecessarily math majors and beginning postgraduate students. You can kind of tell my target audience from the daily quiz I post on the community tab. These are considered as prerequisites for understanding much of the material and activity going on the channel, which comprises of calculus, linear algebra, and set theory, some basic proof writing skills, although we're doing a bridge course on proof writing right now on the channel, Introduction to Proof and Analysis. So it's here, just in case you guys didn't know about. Where's my channel? Okay, hang on. So yeah, there's a bridge course on the channel on how to do proofs, because I know some of my audience came from non-math background and may have not yet taken a formal proof-based math course. So this series is for them. So if we go to the this playlist, let me just find the playlist here. Yeah, this one right here. It's called Introduction to Proof. So this is not a traditional Introduction to Proof course, because I really want to get into the actual stuff that you're interested in, typically interested in, namely actual literature on, say, for example, probability, statistics, differential equations, stochastic process, that kind of thing. Okay, so for that, a common denominator is basic real analysis. So this is just introduction to proof for its own sake. It's for people to help people to get into analysis as soon as possible. The basic language of analysis, limit and continuity, metric spaces, that kind of stuff. So we won't be just using one single book, but instead we will just see through examples from, for example, here we're doing the Zurich mathematical analysis, underrated textbook in the Western world. Say, for example, we discuss limit and continuity, Cauchy sequences, right? And really you just practice proof by reading proofs. Okay, we'll introduce how the proof works, but we won't spend too much time on the elementary stuff. Okay, we'll see how proof works and then get into some actual real analysis very shortly. Right. So this is ongoing, typically in the morning. And yeah, so there's that. Typically, advanced undergraduate students are well equipped to study this, even without a math background, formal math background. As far as chat is concerned, could you please recommend easy to follow resources for starting with measure? Øksendal, basically the one we've been doing. Øksendal is perhaps, the thing is, do not look for easy to follow resources, because measure theory is not easy by definition. And that being said, Øksendal is perhaps the most approachable. The subject itself, by its nature, is hard. And I always believe that it is a wrong-headed approach to make math quote-unquote easy, because math is hard, and people can do hard things voluntarily. You just need to show them, you just need to carve a path. Right? So there you go. So this is, do not expect Øksendal himself said it. You're about to get immersed into some serious mathematics. That's what he said in the preface. And the same author of the beloved Linear Algebra Done Right, by Øksendal. You're about to immerse yourself in serious mathematics. So yeah, this is not easy, but this is a path. This is an approachable path. And Øksendal also gave the supplement for some preliminary stuff. And also, well, we're also doing preliminary stuff. So there is a path. No promise of easy to follow is given, but this is doable. Okay. In fact, my video on measure theory is called Measure Theory Made Doable, not Measure Theory Made Easy. Okay. So, yeah. P.R. Holmes written a text on measure theory. Yes, that's an old but gold one. Holmes is a great writer. But perhaps for modern students, just the organization and time and typesetting is concerned, and the pace as well. I think Axler is perhaps better than Holmes. From pedagogical reason, not for mathematical reason. Okay, Axler is, I think, very suit. If you have experience with linear algebra done right, then Axler, you know what to expect with Axler. It's rigorous, it's great, the exercises are reasonable. So, yeah. This is the number one resource I recommend. So the notation is old, but the treatment is thorough. Yes, that's what I mean, right? The notation is old. You need to probably do some translation for the notations. Right? Paul Holmes' book is always worth checking out. Like he wrote the first book on linear algebra, didn't he? Called Finite Dimensional Vector Spaces. Once again, the mathematics is very thorough and concise at the same time, so it's somewhat paradoxical combination. You'll see it when you read it. And the notation is somewhat old. Terminology is somewhat old, but the math is very solid. Okay. Anyway, yeah. So we're doing weekly measure theory lives. Yeah, if you have time, try to follow that. Currently, we're in chapter 2, middle of chapter 2, because constructing measure is always the most difficult part when it comes to measure theory. So measure theory has this kind of a initial barrier of entry on its own. Okay, I mentioned SDE has a big barrier of entry because of measure theory, and measure theory itself has a big barrier of entry because of chapter 2. Constructing measure is a highly delicate business, and once you have measure, integration is relatively easy because you get this nice convergence theorems. Bugachev's measure theory is self-contained, can have pretty much all you need to know about in the chapter. That's a Russian style. Perhaps we'll do a Russian style measure theory sometime as well. But definitely when it comes to approachability, Axler's book is perhaps, I wouldn't say the most approachable, but definitely it is up there. Okay. If you're new to analysis, still, if you're new to analysis, I would still regrettably argue that you have no business in measure theory. If you're completely new to analysis, let's say you don't know how, for example, Cauchy sequence work, and you're having trouble with proving a limit statement, then I'm pretty sure you have no business in measure theory. Okay, it might sound depressing, but the good news is it's not that difficult to catch up. It's not that hard to catch up. So you can use the bridge course, okay, and as well as Axler's own supplement to catch up. Because Axler himself said you need to have a basic understanding of an analysis. The prerequisite for using this book include a good understanding of elementary undergraduate analysis. Just want to set the records, okay? Because sometimes you will see math book says, oh, nothing is assumed except for mathematical maturity, except you need to know analysis and group theory. Right? I don't want to do that, okay? So you need to have a good understanding of elementary undergraduate analysis. I like this. It's completely honest. I don't want you to enter the book and have your confidence completely shattered because you don't have the background. Right? So here you go. Yes, What it means, you are completely right. It is entirely possible to formulate the Black-Scholes equation without applying martingale framework. Exactly. It is possible. And we will do it that way. And we'll do it because, well, I haven't covered martingales in much detail, if any. I mean, I only mentioned martingale once in my stochastic series. It is possible. Yeah, we can do the Black-Scholes equation. We can do the Black-Scholes equation, get the Black-Scholes formula without applying martingale framework. Yeah. It's a matter of preference because physicists tend to actually understand martingale. Sorry, physicists tend to understand Black-Scholes without martingale, whereas financial mathematicians and probabilists like to use the martingale framework. Both are equally valid. And we will do the one without martingale first, simply because we have not yet covered much martingales, but we will do so. Okay, so that's, I guess, enough like overview. So let's get into the main paper we're going to do. Okay, so we have aimed to keep the theory to a minimum. However, we rely on a basic assumption that the reader has at least a superficial feel of random variables, okay, which I assume everyone in this chat have. Independence, expected value, and variance. Okay, and in particular is familiar with the concept of a normally distributed random variable, which I also assume everyone have. Our numerical experiments use a Monte Carlo approach. Okay, so Monte Carlo means random number generation. Random variables are simulated with a random number generator, and expected values are approximated by computed average. This is typical for Monte Carlo simulation. Monte Carlo simulation is all about generating a bunch of random numbers, transform those random numbers by some deterministic procedure, and then calculate sample statistics. Okay, so that's the Monte Carlo method in a nutshell. The best way to learn is by example. So we have based this article around 10 MATLAB programs. Actually, unfortunately, I don't have MATLAB installed on my PC because I have lost my student license years ago. And well, but the thing is, the programming language don't matter. It's algorithm, right? So try to understand the algorithm. And using the philosophy similar to 14, I think that's their book. Let's look at 14. Reference 14. Oh, spectral method in applied math. Okay, so that's a spectral method in MATLAB. That's a linear algebra thing. Anyway, it don't matter. Let's go. It's similar in philosophy, not in content. Okay, let's go. To make the programs downloadable, so here there's the website. Did I put the paper in chat? Guys, did I put the paper in chat so you can go to the website yourself? Oh, what's going on? All right, let's let it load. Hopefully the MATLAB files are still here. Make the programs downloadable. MATLAB is an ideal environment for this type of treatment. Not least, damn, the link is dead. Well, that sucked. Okay, we do the best we can. Not least because it's a high-level random number generation and graphic facility. Once again, it's not the most essential thing. Right? What matters is the algorithm. The programs have been kept as short as reasonably possible and are designed to run quickly, less than 10 minutes on a modern desktop machine. To meet this requirement, we found it necessary to vectorize the MATLAB code. These are coding details. Okay. We hope that the comment lines in the programs in our discussion for key features in the text will make the listing comprehensible to all readers who have some experience with a scientific programming language. Yeah, you can use Python or whatever you like. In the next section, yes, finally, the math. Time to get excited. Guys, why do you keep retracting messages? Because I'm reading the messages. Yeah, Python is a reasonable substitute. Yeah, NumPy is perfect. Once again, this is not essential. Programming languages come and go. Math stays forever. We're gonna keep our eyes peeled for math. An algorithm has no place on a machine unless it already lives in your mind. Okay, so in the next section, we introduce the idea of a Brownian motion and compute discretized Brownian paths. In section 3, we experiment with the idea of integration with respect to Brownian motion and illustrate the difference between Ito and Stratonovich integrals. So these are two main stochastic integrals, Ito integral and Stratonovich integrals. And luckily, to describe those two integrals, you do not need measure theory. It is for proving the properties of these integrals that where measure theory is needed. This is not a special case. This is a common misconception for beginners and people who aren't familiar with stochastic integrals. They thought they were some kind of special Lebesgue integrals, which they aren't. Okay, these can be understood without measure theory. It is for proving the theorems about them where you need measure theoretic probability. We describe in section 4 how the Euler-Maruyama method can be used to simulate SDE. We introduce the concept of strong and weak convergence in section 5. Okay, strong and weak convergence, important. And verify numerically that the Euler-Maruyama converges with a strong order. Okay, so this is a result. This is a theorem. So EM method, not expectation maximization, Euler-Maruyama, converges with strong order 1/2 and weak order 1. In section 6, we look at Milstein's method, which adds a correction to EM. So that's a improvement of EM. But EM is really the mother of all simulation, of all SDE simulation. Well, Euler's method was the mother of all ODE simulation, so this is kind of expected. In section 7, we introduce two distinct types of linearity for EM method. Linear stability. So this is pretty much where in the deeper territories of numerical analysis. You may skip this for the first run. So numerical SDE is its own distinct field. Okay, but for first introduction, pay attention to the fundamental definitions, modeling, and just at least one. Okay, at least one numerical method is enough. Okay, no need to go super in depth when it comes to analyzing numerical algorithm. In order to emphasize stochastic calculus differs fundamentally from deterministic calculus, we quote and numerically confirm the stochastic chain rule. Which is the Ito's formula, aka Ito's Döblin formula. Okay, but here this is just a quote, understanding the statement, and the numerical verification, experimentation. Okay. Section 9 concludes with a brief mention of some other important issues, many of which represent active research area. Okay, cool. Okay, so we will give the definition of Brownian motion, and I will provide some concrete example of SDE in our notes. Okay, I will be writing some notes today. Okay, online Octave uses the same language in MATLAB and it's free. Okay, good to know. Good to know. Thanks very much. Okay, so let's continue here. Rather than pepper the text with repeated citations, we will mention some key sources here. For those okay, so these are some resources. I will not repeat them. Okay, so let's start with the actual math, because it's about damn time. Brownian motion. Brownian motion, we've been talking about Brownian motion from the physics perspective, right? So it started as a model for random motions of pollen grains immersed in liquid. And pollen grains are observed to have this random trajectories, which seems to be nowhere smooth and completely unpredictable. Okay, so that's a Brownian motion in nature. But Brownian motion in mathematics is a stochastic process. That is a time-dependent random variable. Okay, so you can think of a stochastic process as a family of random variables indexed by a parameter. And now here the parameter is t, and t ranges from 0 to t. Now, t is a continuous parameter. For each little t, wt is a random variable. Okay? So a scalar standard Brownian motion or standard Wiener process over 0 to big T of a random variable wt that depends continuously on little t in the set 0 to big T and satisfies the following three conditions. Okay, so first you have w0 equals 0. So the process starts from 0. Actually, you know what? We need to write our notes. Here. First, start with Brownian motion. Definition. Brownian motion. Mathematical definition of Brownian motion is a stochastic process. Now, this is introduced in our episode 1 of the stochastic calculus series. Standard Wiener process. I think that video is my most watched video, about 70,000 views right now. Okay, so that's the standard Brownian motion and standard Wiener process. Okay, and that video is about Ito's integral, and in which we introduced Brownian motion. Okay, so Brownian motion wt, t is in 0 to big T. It satisfies these properties. So first, w of 0, at time 0, the initial position is 0, okay, with probability 1. 2, okay, 2, it talks about the increment. It says, so for a time interval, 0, between 0 and big T, so let's say this is 0, this is big T, you have a sub-interval, s to t. So over this interval, the Brownian motion will experience a change, right? The increment. So for s greater or equal to 0, less than t, less than or equal to big T, the increment, that is w of t minus w of s, okay, this is a random function. The increment over that time period follows a normal distribution. Follow a normal distribution with mean 0 and variance t minus s. Okay, so the key observation is that the variance is linear in the duration of the time interval. Oh, hi. This was motivated in our stochastic calculus series, but basically, in a nutshell, the reason we chose this definition is so that Wiener process is a continuous analog of symmetric random walk. So in a discrete setting, okay, where you have a random walk over the lattice of integers, it works like this. At any position, at each step, the Brownian walker, random walker, Brownian particle, either move to the left or right with equal probability. And in that construction, the variance is proportional to time, and here in a continuous analog, we also assume the increment is linear in time. And that's the motivation for choosing this definition. Okay, and here the increment also follows normal distribution. Equivalently, Wt minus W of s follows the distribution square root of t minus s times standard normal. Okay, so I assume everyone knows how normal distribution works, so I will not explain why you need the square root sign. Okay. Okay. Third, this is the independent increment property. Third is called independent increment. So 2 is about normal increment. Yeah. Normal increment. And third is about independent increment. Independent increment property says, okay, if you have two time intervals that aren't overlapping, let me draw the picture. So this is 0 to big T again. It says S is less than T, U is greater than T, and V is greater than U. So now you have two time intervals that don't overlap. The independent increment property says if the two time intervals don't overlap, then the increments over the two time intervals are statistically independent, are independent random variables. Sorry, I'm having some voice issue this morning. Yeah, so it basically says W of t minus s minus ws, that's the increment in s to t, and W of v minus W of u, that's the increment in the second interval. Those two are independent. So the independent increment property says if time intervals don't overlap, then increments are independent. Okay, so there's that. That's the definition of Brownian motion. From this definition, it is possible to show that the trajectories of Brownian motion is continuous with probability 1. Okay, so the thing is, for stochastic process, you have in practice you can characterize them in a 2x2 table. So the state may be continuous or discrete, and time may be continuous and discrete. So it is possible to have continuous state, discrete time. Let me say, this is state can be discrete or continuous. Time can also be discrete and continuous. And Brownian motion falls into this category: continuous time, continuous state. Okay, and the other entries are also very useful as well. Discrete time, discrete state. You have the Markov chain, discrete time Markov chain. Discrete time Markov chain. For example, discrete time continuous state, that's for example the ARMA process. ARMA process in time series analysis, autoregressive moving average. That's a discrete time continuous state stochastic process. And you also have continuous time discrete state, for example the Poisson process. But here we're dealing with Brownian motion. Okay, these are just examples. There are many of them. Okay. The study of stochastic calculus, a stochastic process, is immensely huge. Are they have connections? Yes, of course, there are big connections. For example, I just mentioned one, right? Random walk on lattice. It is a discrete time discrete state continuous, discrete time, discrete state stochastic process, and its limit is the Brownian motion. So you can often simplify the analysis of a discrete process by looking at its continuous limit. I will say that again. Sometimes you can analyze a discrete time process by looking at its continuous limit. And also you can understand a continuous process. You can understand the intuition of a continuous process by looking at its discrete counterpart. If you want to see how they are connected, well, let me give you an example. One of the videos I post is called Brownian motion and heat equation. We constructed Brownian motion, well, informally, from random walk, from a discrete process to Brownian motion. Where's my playlist? Yeah, this is the course, I believe. It's in the course tab. Go to Stochastic Calculus for Absolute Beginners, View Full Course, the last one. Here, it's in the thumbnail. It's in the thumbnail. The discrete process, the discrete random walk, right? As delta t goes to 0 and delta x proportional to the square root of delta t becomes a continuous stochastic process. That's the Brownian motion. And suddenly the heat equation appears. Okay, so check out this video. I'll share it, because I'm a self-absorbed YouTuber who cannot help but stop promoting his stuff. Okay, anyway, let's go. So let's take a look, right? That's the definition of Brownian motion. So for computational purpose, it is useful to consider discretized Brownian motion. You see here, where after introducing the continuous model, we immediately introduce the discrete version, discretized version, because it's useful for simulation. So where Wt is specified at discrete t values. Right? So we set delta t to be big T over big N for some positive integer n. Okay, so here in the picture, discretized Brownian motion works like this. So you're going to discretize the interval 0 to big T into smaller time intervals. Delta t is big T over big N. Just chop them into tiny little subintervals. Okay, and over each subinterval, we can label the time as tj's. This is t1, t2, and so on. And tj is j times delta t. That's tj. Okay, so little j runs from 0, 1, all the way to big N. So that's the discrete time. And over each time interval, you can just simulate normal random variables. So this way, you can simulate increment over each subinterval, and now you can stitch them together to get the simulated trajectory. Yeah, condition 1 says start with 0. Right. Condition 1 start with 0. So here you get an algorithm, the MATLAB code, but it's easy to read. Okay, so here you can say set the state of random. The rand_n function is, I think rand_n is it generating normal random variables in MATLAB? I'll answer the question about Poisson process later, but I just want to finish this. Okay, so here, what is this doing? Actually, here, let's read the text here. So it says, condition 2 and 3 tells us the new position of the Brownian value, right? The new state, Wj, is the old state plus the increment. and the increment is independent random variable of the form delta t square root times normal 0, 1. And that's exactly what happened. So here, you start with the first increment, dw1. dw1 is the square root of dt. Square root of dt is the standard deviation of dw1. And then times ran n. That's a standard normal random variable. Yes. Ran n generates 100 independent standard random variable. Yes, ran n gives normal. Yeah. And now we calculate the next. We have w1. At time 1, this is just the dw1 because it's 0 plus dw1. And ran gives flat. Okay, that's so ran without n is uniformly random. Okay, thanks very much, Atomos. Okay, so here we have this formula for dwj. Wj, this is the exact formula. So every time you just add a little increment to it, start from 0, okay? And dw1 is square root of dwj. Okay, dwj is delta t, very small, times the normal 0 random variable. Okay, so this size is, so discretely speaking, you don't know the detail inside, right? So you can only draw a straight line segment. So it goes from here to here. The height is dw1. And dw2 might be this. dw3 might be increment like this. Right, so basically, yeah, that's the formula. Wj equals Wj minus 1 plus dwj. Okay, so Wj is a shorthand for the continuous function w evaluated at tj. Okay, so this way you can simulate Brownian path. So with this skill, you can already do stochastic integration. Because once you know the dw's, you can do stochastic integration, like Ito integrals, Stratonovich integrals, and things like that. So this is the first step towards understanding stochastic calculus and SDEs numerically. Okay, I think this should be pretty easy to understand. Okay, we have the technology to generate normal random variables. Without, you can ignore the details. Okay, these are built-in functions. Hi Sunday, thank you very much for joining the stream. Okay, so we finished describing that, and let's come back to chat. Somebody asked, Euler, my boy, great name, asked, is the Poisson process some kind of random crossing counter? I was thinking of atom decay. Yes, exactly. Yes, exactly. So Poisson process is different from Brownian motion. And a great example is exactly as you said, atom decay, like a Geiger counter. Okay, so without getting into the atomic physics, let's just give a much simpler example. A Poisson process is kind of an arrival process. Okay, it models the arrival of a customer to a coffee shop with two fundamental assumptions. It counts the total arrival over time, so it cannot decrease. It's like counting views on YouTube. Okay, counting views on YouTube. Like I cannot help but scroll analytics, doom scroll analytics every 5 minutes. So basically, I'm watching the progression of a Brownian motion, not a Brownian motion, of a Poisson process. So right now I'm at exactly 400 views. This is a Poisson process. This is a counting process. Okay, views came in only one at actually. It came in 6 at a time. Okay, I don't know why, but theoretically speaking, the Poisson process only increased 1 at a time. So Poisson process is here, right? So it's continuous time and discrete state valued. This is a Poisson process. Stock price is a Brownian motion. I mean, it's a geometric Brownian motion. We'll talk about what that means. So, okay, so that's discretized Brownian motion. And you can use this method just purely from the definition to generate Brownian paths. Okay. And it's a great exercise to write the update formula in your preferred programming language. Let's go. Okay. So yeah, and also here you have explanation of MATLAB. Wow, that's amazing. The MATLAB file mfile bpath1.m in listing 1 performs one simulation of a discretized Brownian motion over 0 to 1 with n equals 500. Here, the random number generator rand_n is used. That's a MATLAB function. Each call to rand_n produces an independent pseudo random number. Wow, this is very approachable. Okay, even explain MATLAB. Okay, from the normal 0-1 distribution. In order to make the experiment repeatable, you can set the initial state. Right? That's basically, sometimes we call it setting the seed for random number generation. Without this line, you can still do rand_n, but the results won't be the same every time. Okay, this way you allow repeatable experiment. Because these are pseudo-random, they aren't truly random. There is a deterministic algorithm to generate random numbers. That's the topic of Monte Carlo simulation, not really about Brownian motion. They aren't truly random. Okay, they are actually generated by deterministic algorithm. They just look like they're random. Subsequent runs of bpath1 would then produce the same output. Different simulations can be performed by resetting the state. Right, so anyway, the numbers from rand_n are scaled. Yeah, this is a crucial scaling factor. That's the definition of Brownian motion. Increment has variance proportional to time. This is crucial. And this is why, actually, this little factor, this innocent-looking factor, is the whole reason stochastic calculus exists. Because of this factor, for more explanation, see my video, Why Brownian Motion Needs a New Calculus. It's because of this scaling factor. Without this scaling factor, you can just use ordinary calculus for Brownian motion. Okay, so extremely important. This way you can use the for loop to do the updates, basic programming knowledge that creates an n×1 array, big W. There is a minor inconvenience. Okay, for me this is natural, but I guess for some this is an inconvenience, because I always see debate whether natural numbers should start from 1 or 0. My goodness. To me, natural numbers start from 1. Okay? I believe this is historical. Okay? People invented 1 first and then defined 0 after. So for me, the first number of humanity is 1. Okay? So I believe this religiously. Okay? Of course, but you can start from 0. It's just a matter of choosing which base case you're using. Okay, I like to think of natural numbers start from 1. Some prefer it start from 0. And as a result, when I translate a piece of MATLAB code to Python, I have to do this conversion. And sometimes, often, I forget about it. Okay, in Python, index start with 0. In MATLAB and R, they start from 1. Anyway, this is a little bit of a small thing to bear in mind when you debug. Okay. Anyway, so here we compute W as W1, W2, all the way to Wn. So initial value W0 is 0. I mean, it's not in the array, right? The array starts from W1. W0 is not included in the picture. For the purpose of visualization, a discrete data have been joined by straight lines, like I did here. Okay. So, and This is the result is called a discretized Brownian path. This array of w's, these are random numbers, w1, w2, wn, is called a discrete Brownian path. Okay, and of course there's some MATLAB programming trick. You want to vectorize your commands so that the algorithm is more efficient, but that's not what we're concerning here. Okay, there are different programming tricks to make the method more efficient because MATLAB is optimized for vectorized operation, but these are not essential mathematical concepts. So that's the simulated trajectory. As you can see, it is extremely rough. Okay, I want to mention this once again. Okay, in my videos, in my live stream, we have said this many times, that the reason Brownian motion needs a new calculus, the reason stochastic calculus exists, Ito's calculus, Stratonovich calculus exists, is not because WT is a stochastic process. Even though stochastic is in the name, the reason stochastic calculus is different from ordinary calculus is not because of quote-unquote randomness, but rather because the sample paths are nowhere smooth. It's the roughness that gives rise to new calculus. It's the roughness that fails ordinary calculus. It is a roughness that fails the chain rule, the product rule, the Newton-Leibniz formula. It is a roughness that Ito's formula arises. Okay, even if this is a deterministic trajectory, to do calculus with this function, you still need a new calculus. It has nothing to do with randomness per se. It is because of this scaling factor square root of delta t that compelled a new calculus, not because of quote-unquote randomness. Okay, it's a great common misconception. Okay, anyway, so here, going to the mathematics. What is a SDE? Well, to talk about SDE, we first need to talk about, here, what's going on? Is this a, yeah, this is a Brownian motion. Why is there an exponential curve? What's going on? What is this saying? BPM, let's look at 3. What's going on? The mean should be 0, right? The mean should be constant 0 by definition, because W of t is the same as WT minus W of 0, which follows normal distribution 0t always, so the mean should be 0. Why there is a deterministic trend? Hold on a second. Why there's a trend in this curve? Not this curve, but this one. What is this saying? Let's keep reading. Okay, I will try to gloss over the programming detail because that's not exact. I mean, we don't want to spend too much time on that. Okay, so you can apply a function to WT as we often do. You can apply a function to WT. Here, you can apply a function, because now you have, let's say you already simulated a discrete Brownian path. You can apply a function to all those Brownian values, u of WT, and u is exponential of t plus half WT. So now you have generated those random W values. This is a deterministic function. So this is a very easy operation. Yeah, just do the substitution, takes exponential, and you will see the average grows smoothly. Even though u of t is still not smooth, the average is smooth. Okay, and we will be able to calculate. Actually, we can calculate it right now. Guys, what is the expected value of u of t? Let's do some math. U of t is the exponential of t plus half WT. What is expected value? This needs a little bit of a knowledge from basic probability. Remember, that's the function. How can you calculate the mean of u of t? Well, that's the expected value of e to the t plus half wt, right? So e to the t is a constant, you factor it out, and then times e to the half w of t. Well, to calculate this, you need a formula called the moment generating function. Recall, the moment generating function, we actually derived the moment generating function on Thursday's stream about integral transform, because the moment generating function is essentially the Laplace transform. Okay, moment generating function of normal mu sigma square is expected value. Let's say x follows this distribution, then expected value of say, let me use the argument alpha. Okay, alpha of alpha times x is e to the mu alpha plus half sigma square alpha square. And here, w of t follows normal distribution with zero mean and variance t. So mu is 0 and sigma square is t. So this is exponential of half t, half t, what's the alpha here? Alpha is 1/4. Sigma is t, sigma is t, and alpha is 1/4, so that's 1/4. So together you should get e to the 9/8t, exponential growth curve. So this blue curve here is this function, e to the 9/8t. Okay, its mean can still be a smooth function. Okay, okay. So here it says note that u of wt in the form of 4.6. Hang on, where's 4.6? What? Yeah, this is expected value. Yeah, we just calculated this using the moment generating function. But here it says what? From the 4.6. What's 4.6? Is that a new section, huh? 4.6 SDE. 4. That's where's 4.6? Is 5.1. 4.6 is here. It's a SDE. This is a what we call a geometric Brownian motion. One of the assumptions in the Black-Scholes model. Okay. Anyway, we'll come back to that. So you can think of this as you can think of this as a stock price behavior. And also we covered geometric Brownian motion in this video. How mean return lies, Ito's lemma second form, GBM, stands for geometric Brownian motion. And yeah, this geometric Brownian motion is on the thumbnail. And volatility drag, episode 4. Okay, so so now we have so far what we've done, right? We've managed to define Brownian motion, and we studied how to simulate Brownian trajectory numerically, right? Of course, that means discretely, and observe some typical behavior, right? These are sample paths, individual sample paths, and the mean of a southern path is a continuous function. It's a smooth function, which we calculated as an exponential function in time. Okay. Oh, sorry. I missed chat. Shit. Sorry, guys. I did that again. Very interesting sex. No worries. My pleasure. Stochastic control is what I wanted. Queuing and operating control system. Yeah, exactly. And stochastic control is a great topic. Now you open a new topic about 1 and 0. I know, right? Fight me. It's intuitive to assume unity first. Yes, that's my I think historically 1 came first and 0 after. So that's my justification for putting 1 as the first natural number. Okay. Okay. I'm not. We aren't doing the proofs using Unicode and whatnot. These are for more specialized tools. I don't want to introduce another extra layer for understanding stochastic calculus because this is quite an already a formidable subject. Right? We want to keep everything as naked as possible. I don't want to dress with an extra layer of prerequisite. Okay. Okay. So here, yeah. For example, okay, this is stochastic integral. Now let's define stochastic integral. Stochastic integral. This is episode 1. This is episode 1 in Ito integrals in particular. But here we actually going to define another form of stochastic integral known as the Stratonovich integral. So the stochastic integral is overall, that's the idea, okay? Because stochastic integral is actually very different from deterministic integral. I will explain that sentence a bit later. Okay. Given a suitable function h, the integral, so remember here, h is just a regular function in calculus. It is deterministic. The integral 0 to t, the integral from 0 to t, h of t dt may be approximated by this Riemann sum. Right? We all know this from regular calculus. Area under the curve. Calc 1, classic Calc 1. So what kind of rule is this kind of approximation? Can you guys remind me? This is a Riemann sum, yeah, but what kind of Riemann sum? Does anyone know the terminology? T1, T2, these are the endpoints of subintervals. So what is this doing? For example, when j equals 0, this is ht0 times t1 minus t0 plus ht of 1 times ht2 minus t1, and so on. What kind of Riemann sum is this? This is a left Riemann sum. This is known as the left Riemann sum. This is critical observation. So for each subinterval, you're using the left endpoint as the sample point for the function. It is not lower sum because lower sum is a theoretical notion. So that says the interval length gets multiplied by the infimum of the function over that subinterval. But numerically, that's awkward, right? Because numerically, to find the infimum, you first need to solve an optimization problem in each subinterval, and which can be very complicated. So we're using the left endpoint. This is called the left Riemann sum. So this is the left Riemann sum, and we can approximate the integral using the left Riemann sum. But this is just a convenient choice. It is a fact from classical calculus, real analysis, that the sample point location should not matter. This integral exists in the Riemann sense if the sample point over each subinterval do not matter. As long as the mesh of the discretization, the mesh of the grid, that is the maximum length of the subinterval tends to 0. The choice of the sample point should not matter. Okay, choosing the left endpoint is merely a convenient choice. It is not a mathematical requirement. You can approximate the same integral using the right Riemann sum. You may use the midpoint rule or the Simpson's rule, right, from calculus. Okay, so that's traditional, regular calculus. Bear that in mind. We'll come back to this in a bit. Okay, so indeed the integral may be defined by taking the limit delta t tends to 0. Yeah, now taking the delta t, that's the subinterval length, tends to 0, this will approach the exact value. In a similar way, oh hi, Abe Buckingham, thank you very much for joining the stream. Yeah, so is this left or right? This is left. This is left. I try to, I just explained this is the left endpoint. See, look at the first term, h of 0, f endpoint times this. What would be the picture for the right Riemann sum? The right Riemann sum takes the right endpoint of each subinterval as its sample point. So the right Riemann sum would have this rectangle, this rectangle, okay, the right rectangle. So this is a left Riemann sum approximation to the Riemann integral. And here it says, in a similar way, we may consider the sum of this form. Okay, so here h is still a deterministic function. H is still a deterministic function. You see, h only depends on t. So h is not random. And it gets multiplied by not increments of t, but rather increments of the Brownian increment, w of tj plus 1 minus w tj. So basically that's the increment that we just simulated here. For example, this is tj, right here. This is tj and tj plus 1. The height increase is w of tj plus 1 minus w tj. Okay? You can multiply, so this will lose the interpretation of area under the curve, but this is still a valid operation. You can multiply the function htj by the increment of the Brownian motion instead of the increment in time. Right. So, which by analogy with 3.1 may be regarded as an approximation of a stochastic integral. Here we're integrating h with respect to a Brownian motion. Okay, I just want to give, hey professor, I'm not a prof, but yeah, you're very welcome to the stream. So, some might wonder why we would be interested in such an expression. Is that just for fun? Oh, not so much, not quite. Okay, and by the way, this is also left endpoint approximation. You see, this is still left endpoint approximation because you're still using h of tj. Looking at the time interval, here we're looking at the time interval tj to tj plus 1. We're multiplying the increment of the Brownian motion in that time interval by the value of h on the left endpoint, h of tj. Still, this is still left endpoint, left Riemann sum. Okay, and this is the definition of Ito integral. Perhaps, because I'm, guys, I apologize for doing this because my voice is shit today. I will play my first video. for absolute beginners. As the name suggests, over them along the way, give a stochastic calculation, and then optimize. Our concept, let's consider technicalities later. Okay. Let's go. To motivate our concept, let's consider a gambling sequence, a spirit true to the origin of probability theory. Let's play a game. At each step, toss a fair coin. In notation, for each I equals to 1, 2, and so on, let's denote delta Wi, a random variable, the outcome of the I's toss. That is, Wi's are IID random variables that takes two values, plus or minus 1, each with equal probability of 1/2. To make the game more interesting, before each coin toss, you place your stake xi minus 1, say in dollars. So, before the first toss, you place your stake of x0. Before the second toss, you place your stake of x1, and so on. If the I's outcome is 1, you win xi minus $1. If the outcome is minus 1, you lose the same amount of money. And here's the diagram. The key is that at each step, the stake is placed before the coin toss. So a natural question is how much money you win or lose after n steps. And the formula is quite straightforward. The wealth after the n step is yn equals to the sum of xi minus 1 times delta wi, where I ranges from 1 to n. Basically, if you win the I step, xi minus 1 gets a positive sign, otherwise it gets a negative sign, and you just sum the whole thing up. And this is essentially the Ito integral in its discrete form. Our goal is to define stochastic integrals in continuous time, something that would look like yt equals to the integral from 0 to t xs times dws, where t is continuous time. The meanings of the integral sign xs and dws are to be specified. But before, so let's stop here. So I just wanted to make sure that this formula is understood. Okay, so in a coin tossed experiment, delta wi is either plus or minus 1 with equal probability. Okay, it's a fair coin. So looking at this diagram here that depicts the gambling sequence. So here you have these discrete steps. You have these discrete steps starting from time 0, and then this is after the first coin toss, okay? And by that time, you already know the outcome. The idea is you place your stake before the coin toss, okay? You place x, say x0. Actually, you place x. You place x1. You place x1, right? No, x0. X0 before the coin toss, before the first coin toss. And say, if you get a head, you win. You win the amount of money that you bet. Okay? And if that's a tail, then you lose the same amount of money. So it's just that the sign of xi minus 1 is random. So therefore, you get an alternating series, a random alternating series. The sign of xi may be plus or minus. And after n rounds, the total wealth is this. Right? This looks like an integral, right? This looks like an increment in the integration with respect to Brownian motion. Okay, so this is what we're trying to get to define. This is the essence of Ito integral, as I said. But now you need to interpret, okay, what is xs, what is dws? Okay, dws is now the increment of the Brownian motion, and xs is the bet. Okay, so next thing let's keep watching this. Times dws, where t is continuous time. The meanings of the integral sign xs and dws are to be specified. But before doing so, we emphasize a key assumption in the stakes xi minus 1. It's called non-anticipation. Xi minus 1 can be almost any function. It can be deterministic or random, but it cannot rely on outcomes of future coin tosses. That would be cheating. Let's look at some common strategies, and we'll see that they all obey this assumption. First, we have the constant stake strategy, also known as buy and hold. The idea is to always bet the same amount. So xi minus 1 is a constant c. Next up, we have an interesting strategy historically called the martingale, or doubling. The idea is you start from the initial stake x naught of 1. If you lose, you double it. If you win, then reset the next stake to be 1 again. So imagine if you place $1 at the beginning, and it turned out that you lost the first round. So in the next round, you double the stake to $2. And if you still lose, you double it to $4, and so on. So the formula for xi minus 1 in this case is 2 raised to the power of li, where li is the length of the losing streak. So xi only depends on the latest consecutive number of losses. It does not depend on the future. Next up, we have the momentum strategy. The idea is to follow the previous outcome. The opposite to the momentum strategy is called the mean reversion strategy, in which you bet the opposite of the previous outcome. Xi minus 1 equals minus delta Wi minus 1. And lastly, we have the proportional wealth betting. The bet is proportional to the current wealth. Xi minus 1 equals alpha times Yi minus 1, where alpha is a constant. If you're rich, you bet more. If you're poor, you bet less. And of course, this is by no means an exhaustive list of strategies. The point is, all of these strategies satisfy the non-anticipation assumption. We have no information about future outcomes when we place our current bet. So with that clarified, let's go back to the main objective, defining stochastic integrals in continuous time. Okay, so here I mentioned that the integrand in the function, in the integral, and indeed, A. Buckingham, you're completely right. This is the stochastic version of the Riemann-Stieltjes integral. Okay, so Riemann-Stieltjes integral is a slight generalization for the, what's that? The slight generalization for, hang on, what's a Riemann integral? Yeah, in Riemann integral you have dt, integral over dt, but you can change dt to d of another function. So that becomes the Riemann-Stieltjes integral. Difficult to pronounce. I believe, Swedish name. Riemann-Stieltjes integral is the deterministic analog for a stochastic integral, dgx. And that's the Riemann-Stieltjes integral. And here g is exactly w. Great point. So, but here we're introducing another key assumption, as I mentioned earlier. The integrand has to be non-anticipating. Here in the paper 3.2, h is a deterministic function. It has nothing to do with w. It is purely deterministic. At each time, you already know how much you're going to bet, regardless of history. Okay, and that is of course non-anticipating. And this is of course non-anticipating. I think I made a quiz. I made a quiz some time ago and asked whether something is an Ito integral, and unfortunately the result isn't very great. Let me just clarify that. Okay, let's go to my community tab, post. Okay. Okay, go to my community tab. I posted like 2 months ago or something, and maybe I should just write it here. So the thing is, I wrote, okay, the limit as delta t tends to 0, the sum of I from 1 to big N, wi, delta wi, that is delta wi, where delta wi is defined as wi minus wi minus 1. I asked in my community tab whether this is an Ito integral, and I believe more than half got it wrong. Why? Because this is not non-anticipating. This is I minus 1 to I. Delta Wi is Wi minus Wi minus 1. And guess what is the integrand? The integrand is evaluated at the right endpoint. This is Wi. So this violates the non-anticipating assumption. I say this again. This integrand Wi is evaluated at the right endpoint and thus violates the non-anticipating assumption. It's like you place your bet after the coin is tossed. Of course, that's just cheating. So therefore, this is not an Ito integral, and all the properties of Ito integrals do not apply to this function. This is from right to left, exactly. That's not right. So chat asks, historically speaking, how was Ito integral motivated? Finance, gambling. Yeah, the one I just mentioned in the video. Yeah. So so that's basically the motivation. Of course, I'm pretty sure there are other motivations as well, simply for mathematical convenience. It is perhaps a great surprise that in stochastic calculus, the sample point matters. Remember, in Riemann-Stieltjes integral, you can pick your sample point Ci arbitrarily. If the integral is well defined, it means here in Riemann-Stieltjes integral, if the integral is well defined, it means as the mesh size tends to 0, the sum converges to a fixed value for all possible choices of Ci. Here it says the limit here is understood to be a number big A, that is the value of the integral, such that for every epsilon greater than 0, there exists a delta such that for every partition mesh P with mesh P less than delta, and for every choice of Ci, the approximation error is less than epsilon. So this basically means you can choose your error tolerance, epsilon, for any arbitrarily small error tolerance. You can make it as small as you like. You can always pick a mesh that is fine enough so that once the mesh size is guaranteed, mesh size is guaranteed to be less than delta, for arbitrary choice of Ci, does not matter how you pick the sample point, the integral is close to the exact value by no greater than epsilon. So that's the key feature in classical integral, Riemann-Stieltjes integral. In stochastic calculus, as we shall see very soon, the choice of the sample point, here we're using the left endpoint. This is not just a mathematical convenience, it is a modeling choice. Here, the non-anticipating assumption is a modeling choice, and this is the dominant choice in finance. In finance, there is something called the called the efficient market hypothesis. Basically, the current price represents all the information useful, roughly speaking. So in finance, you almost always see left endpoint approximation, aka Ito integral. That is a modeling choice. And besides that, there is also a mathematical reason. If you change the sampling point to, say, Cj, an arbitrary point between Tj to Tj plus 1, then the integral value would depend on the choice of the sampling point, even when the mesh size tends to 0. Let me say that again. Here, if we replace the sampling point to be an arbitrary point inside the subinterval, the resulting limit would depend on the sampling choice, a highly unexpected result. Okay, let me just grab a cup of water and I'll come back and write some notes. Okay. Yes, Stratonovich samples from the midpoint, exactly, which we'll come to next. The point is, that's a modeling choice. Stratonovich rule samples from the midpoint. And in fact, you can sample from arbitrary point. This means there's actually infinitely many stochastic integrals. The sampling point choice will affect the final integration outcome, the limit outcome. Highly non-trivial fact. Okay. Okay, now I'm back. Yeah, EJ says diffusion equation does not satisfy special relativity. I mean, when delta t tends to 0, the probability of infinity, yes. Yes, this is a very deep comment. Yeah, basically in diffusion equation, you have, quote unquote, essentially infinite speed of information propagation, which is unphysical. So therefore, diffusion equation is only an approximation, not actual physics. Anyway, all models are wrong, some are useful, as statisticians often say. Okay, so now let's write some note. Stochastic integration. Yeah, that's my cat. Stochastic integration. So this means not all stochastic integral implement the non-anticipating assumption. Exactly, you're completely right. For example, Stratonovich is not non-anticipating. Stratonovich is very much not non-anticipating. Okay, only Ito integral satisfies the non-anticipating assumption. Okay, definition. Okay, so why don't we consider just a deterministic function? Let g of t be a deterministic function. Function of time, just like in the paper. Okay, and Wt is the Wiener process. Brownian motion, Wiener process. Okay, so our goal is to define the expression, the integral from 0 to, say, t0 to t of g t prime dw of t prime. We want to define the expression and see what kind of issue we may encounter. Let's go. So for that, let's draw a picture. This is a picture. So here you have a freaking cat, man. T0, T1, T2. He wants to play. My goodness. I'm doing math. Leave me alone, okay? I'll play with you after. I'll give you catnip. Okay. All the way to Tm minus 1. And here's T. Which book is this on? This is not a book. This is a paper. This is a paper. I give it... let me just put it in chat again. This is a paper by Desmond Hayam. Okay. Desmond Hayem, British numerical analyst. Go to his Google Scholar top paper, An Algorithmic Introduction to the Numerical Simulation of Stochastic Differential Equations. Okay, put it here. Put it in chat. Flop, this is a paper. Okay, so here we're writing our own notes. I was trying to make the point that defining stochastic integration has a crucial feature that is different from regular integral. The sample point position matters, and the choice of sample point dictates which kind of stochastic integral you define. In the Ito integral, we use the left endpoint convention. So, okay, so here, this is the function g. This is a function big G, okay? And so we divide, what I just drew is divide the interval t0 to t into subintervals. Okay, they don't necessarily need to be equal length. Okay, it doesn't necessarily need to be a regular partition. You just need to be divided into a bunch of subintervals. So t0 is less than or equal to t1, less than or equal to t2, less than or equal to all the way to tn minus 1, less than or equal to tn, or just t. Okay, just t. So, and also we have intermediate points or sampling points. Sample points, aka intermediate points. In general, you can use any intermediate point you like, right? So let's draw that. So this is tau 1 and tau 2, tau 3. Actually, yeah, tau 2, tau 3, tau 4, tau 5, all the way to tau n, tau n. These are the intermediate points. Okay. Cat is very angry, as you can probably hear. He's very pissed off that I'm not playing with him. I know, right? He is so chatty. I'm just one. I have two, okay? The guy is very chatty. The girl is not. Okay, so here, this is a, we draw the sample point, and it is defined as, in general, the pattern is tau n, tau I less than or equal to ti, less than or equal to ti minus 1, right, in the picture. So we want to define S as the integral. So S, we want to consider the sum. Consider the sum. Call it, let's call it Sn. Okay, Sn is the sum of g evaluated at those intermediate points. So basically, you're substituting tau 1 into g, tau 2 into g, tau 3 into g. These are the approximate value of g. You're not multiplying that by the width of the interval, but instead multiply that by the increment of the Brownian motion. Okay, so do this procedure. Evaluate g at tau I, and then multiply by the increment of the Brownian motion, which is w of ti minus w of ti minus 1 quantity. Okay, so that's the sum, and I goes from 1 to n. So let's consider this sum. Okay, so, well, what can you say about this sum? What can you say about this sum? So, the thing is, this sum right here, okay, this sum right here, the observation we are going to show is that in general, okay, Sn not only depends on n, it also depends on tau I. Sn depend on tau I. Not just Sn, the limit of Sn. Because eventually you want to take the limit, right? You want to take the limit so that the mesh tends to 0. So the limit of, say, let's call it the mesh. Mesh is defined as a maximum of ti minus ti minus 1 over I greater from 1 to n. The maximum of the subinterval length. Even when mesh size tends to 0, the limit of Sn still depends on the sample point. Why? Okay, the reason. Here's the reason. Let's consider a special case. So let's consider a special case where G is just W. Okay, so earlier I said G is a deterministic function. Let's just remove that. I mean, it can be random. They just call it a function of G, of T. Okay, so consider the special case GT equals WT. Okay, and then let's see what happens. So in that case, Sn, by our definition, is the sum of I from 1 to n. Okay, you need W of tau I times W of Ti minus W of Ti minus 1. Right? According to this definition, this is what you get. And can we calculate its average? Let's try to calculate its average. Okay, let's use the, because I've been using this physicist notation, so let's now come back to statistician's notation. Expected value. Expected value of Sn. Is stochastic process worth learning? My answer is fuck yeah, but it really depends on what you want to do. Okay, so that's the in a nutshell. Okay, but basically, if you are interested in finance, in physics, mathematical biology, chemistry, control theory, signal processing, you need stochastic, machine learning and data science, obviously, statistics. Stochastic process is worth learning, which is, why this channel exists. Okay, so yeah, that's the expectation. So you get the, and also information theory as well, totally true. I from 1 to n. Expected value of W tau I times WTI. Okay, let's do the expansion. Minus the expected value of W tau I times W of Ti minus 1. Okay, so now we're trying to calculate the expected value of the product of two Brownian motion. Right. For that we need a property. Let's just show it on the side. Okay, so let's consider this situation. So you have, say, this is S and T, and this is 0. What is the expected value of W of S times W of T? There's actually a very simple answer, because remember, we have the independent increment property. So assume S is less than T. Okay? Assume S is less than T, then you can write WT as WS plus increment. So it's WS plus plus increment. So Wt equals W of s plus the increment. So that is W of t minus W of s. That's the increment. And together take the expectation. Okay, so let me just change the writing a little bit. Yeah, so that's Ws plus increment. And then expand that, you get the expected value of Ws squared. And then plus the expected value of W of s times W of t minus W of s. But we know W of s is independent of the increment. The intervals aren't overlapping, remember. You have the independent increment property, so the second term automatically cancels. So this is just expected value of Ws squared, which is the same as the variance of W of s. But what do we say about the variance of Brownian motion? That's just equal to s. So in this case, s is less than t, so you can easily get the situation where t is less than s. So overall, for arbitrary s and t, the expected value of W of s times W of t is the minimum. This is the minimum of s and t. So this is the formula, okay? So this is quite useful in Brownian motion in general. Second moment. Okay, this is actually called the correlation function. This is a correlation function of Brownian motion. Okay. So, yeah. You know, stochastic process is one of those fields of applied mathematics that just screams immediate application, because wherever there is randomness, there is stochastic process. Wherever there is randomness over time, there is stochastic process. It's kind of self-explanatory. So I was doing the complex variable stream yesterday. I was saying something like this. So complex variable is a field, kind of like real analysis, that the immediate application is not clear. But as long as you enter the blue water territory of mathematics, they show up everywhere. Whereas things like differential equations, stochastic process, probability, and stats, they scream immediate application. Okay, so it feels pretty obvious to me that this is completely worth studying if you're interested in applied mathematics at all. Okay, so anyway, coming back to this expression, what can we say? Because notice, this is a situation. Over the I sub interval, you have ti minus 1 on the left end and ti on the other end, and tau I is in the middle. So you can easily tell which number is the biggest. Okay, so by our formula, the second moment is what? The second moment is here. This is the minimum of tau I and ti, which is just tau I. So the first term is tau I. And the second term is what? The second term is ti minus 1. Because ti minus 1 is less than tau I. Okay? So that's the expected value. So that's the expected value. So something, you see, tau I is here. Tau I is here. If we, let's say, and now if we let's say tau I is equals say a weighted average, okay, a weighted average of the left and right endpoint, in which case you can write it as alpha ti plus 1 minus alpha ti minus 1. And of course, as we've seen in our video, when alpha equals 1, when alpha equals 0, then you get Ito's rule. When alpha equals 0, that's the Ito. You get Ito integral. because in this case, tau I is just the left endpoint. But in general, it can be any point in the middle. So, and let's actually fix the proportionality constant. Let's fix alpha. If we fix alpha, if substituted in there, what's the expected value? The expected value of Sn is the sum of I from 1 to n, substitute tau I inside, you get alpha ti plus 1 minus alpha times ti minus 1 minus ti. So this is what? Ti minus 1 cancel. So this is sum of alpha ti minus ti minus 1. But alpha is a constant. Here we assume alpha is a constant, okay? And you can take out alpha. So this is alpha of ti minus ti minus 1. But what is this? This is the total length of the interval, which is big T. Or you can write it as final time t minus initial time t naught. So the result is alpha times t minus t naught. So it is clear that, you see, this thing has nothing to do with big N anymore. Even if you take big N, even in the limit, n tends to infinity. Okay, even in the limit when n tends to infinity, meaning the partition gets infinitely fine, the limit of ESN is alpha times the big T, depending on the alpha. Yeah, parameterize, exactly. Parameterize the sample point on the interval. Alpha is the parameter. It depends on alpha. So therefore, this is a crucial distinction between stochastic integrals and deterministic integrals. So in the Riemann integral, we emphasize that again. We say that the Riemann integral, Riemann-Stieltjes integral exists if the limit of the partial sum, if the limit of the approximating sum, known as the Riemann sum, does not depend on the sample point Cj. Right? In traditional Riemann-Stieltjes integral, as long as the mesh size is small enough, the approximation is the same for all choices of intermediate points. But here, we give a simple example, and we can see even the average depends on the sample choice, the choice of the sampling point. So therefore, you have to make a choice when it comes to choosing the sampling point. And in Ito's integral, we choose alpha equals 0, which means we're choosing the left end point. Ito integral always uses the left end point. This is how Ito integral later has the martingale property. Without it, the property collapses. For Stratonovich integrals, you choose alpha equals 1/2. That is the midpoint rule. That's another popular choice. Ito's integral is the dominant form in finance. Stratonovich's integral is the dominant form in physics. Although, later it turns out, it does not really matter because the calculus for Ito integral and Stratonovich integral can be converted to each other. So it's not the mathematics that matters. Okay, mathematics is different for each type of integral, but they can be converted into one another. Ito and Stratonovich integral. It is the underlying assumption, underlying physics that matters, because in finance we have the so-called efficient market hypothesis. Basically, it says the current price represents all available information. So in finance, you will almost always only see Ito integral. It's like in our gambling example in the video. Right? It's like in our gambling example in the video, because you cannot see the outcome of the coin toss before placing your bet, because otherwise it would be cheating. So that's why in financial application you always use Ito integral. And here in the paper, yeah, so this is an illustrative example, okay, why stochastic integral depends on the choice of the sampling point. This is an explicit example. Everything has an analytic formula. Right? Even the mean depends on the sampling choice. So there's that. Okay. So here in the paper, Hi-M chose the most popular choice. That's the Ito's integral. We use the left-hand point. Okay. Ito's what's that? Ito's lemma, right? Ito's lemma, the stochastic chain rule, is also a consequence of the choice of the left-hand point. Okay. So there's that. Okay. So now we can see here. Let's say you can approximate this already, right? Because earlier we know how to simulate Brownian trajectory, and now you just substitute pretty much the exact formula, and you can calculate the integral. So in the M file, sint in listing 4, we created a discretized Brownian path over 0 to 1. Delta t equals 1 over 500, so 500 subintervals in our definition to form this sum, where h of t is w of t, exactly the same choice that I made earlier. Okay, so now you, come on, yeah, so you just multiply the function wt by the increment. See, here, you see, it uses w of j minus 1 times dwj. Look at the formula earlier. What's the dwj? Dwj is the difference between wj and wj minus 1. So we're using non-anticipating assumption. This is tj, this is tj minus 1, this is tj. Okay, wj minus 1 gets multiplied by the change. Left-hand point, Ito integral. Same thing. So we're simulating Ito integral using the exact formula. Okay. And the sum function is then to perform the, this is MATLAB code. Okay, it does not matter. It produces a random value. Right? So Ito's integral is determined by the Brownian trajectory. If you have the Brownian trajectory Wt, you can compute. Right? If the Wt is given, right, if the function is given, Wt sample path is given, then Ito integral is a deterministic value. The randomness comes from the sampling, the Brownian trajectory. That's the Ito's integral. And of course, here somebody already mentioned Stratonovich rule. You can use the midpoint. You can use the midpoint to approximate the integrand as well. This is also a Riemann sum approximation, and the corresponding alternative, right? So this is regular calculus. You see, this is not the increment in W, but simply the increment in T itself. So that's the regular calculus, right? We know that from regular calculus, midpoint rule, left endpoint, and right endpoint, they're all equally valid Riemann approximation. But here, there's a fundamental distinction between 3.2 and 3.4. 3.2 is Ito, and 3.4 is Stratonovich. And their calculus are completely different. So for Ito's calculus, you need a new set of rules for manipulating a derivative. Like you need the Ito's formula, that's the stochastic chain rule. You need the new product rule, a new fundamental theorem of calculus. But for Stratonovich, a nice thing about it is that regular calculus hold. You can still use the same chain rule. Okay, so this has major ramifications, of course. So, for example, if you are interested, there's also stochastic calculus on manifold. Right, so we discussed information geometry a few weeks back. So imagine now the Brownian motion takes place not in Euclidean space, but over a surface. Right? In differential geometry, we prefer rules that and operations that don't depend on the choice of coordinate system. But unfortunately for Ito calculus, that is not possible. For Ito calculus, its own chain rule, the Ito's formula, is not coordinate independent. So to do stochastic calculus on manifold, typically we choose Stochanovich version because the regular calculus rule survives. Okay, but that's an interesting digression. Okay, we're not going to do stochastic calculus on manifold anytime soon. Okay, so just something that to bear in mind. These are the two most popular choices. In the bottom line, Ito uses left endpoint, Stochanovich uses midpoint. Okay, so here, in a case where h of t equals w of t, the sum of 3.4 requires w of t to be evaluated at the midpoint. Okay, so when h equals w, the Brownian motion again, it can be shown that so w of the midpoint, that is tj plus 1 over 2, w at this point is approximately just the average of tj plus w of tj plus 1 plus a higher order term plus O delta t squared by adding an hang on a second, is that OT or OT squared? I think it's OT squared. Let me check my book here. Yeah, basically the same book, the book written by the same author, also I am. Okay, let me check my book here. Is that a higher order term in? Oh, actually not. Yeah, higher order term in delta t, not delta t squared. Higher order term, little o of delta t. So basically it means it can be ignored. Actually, speaking of that, whether a term is ignorable, I need to get back to the video I posted. Okay, I need to get back to the video I posted. So to illustrate why 3.2 and 3.4 give fundamentally different results, let's look at an experiment. Okay, let's look at an experiment, a toy example once again. This is the second episode. Okay, so this is the second episode. By the way, yeah, we just want to first go to the definition of Ito integral. Here, let me rewatch this and we'll get to the second episode, which talks about why the Brownian motion, in particular Ito calculus, needs a new calculus. Right? Ito's integral need a new calculus. Okay, so this is a continuous version of the discrete sum we talked about earlier. Say from 0 to t, integral. Chain rule, new product rules, and so on. And now we're ready to define the Ito integral. So consider a time interval, say from 0 to t. We first divide it into n subintervals, each one with length delta t, that is t over n. And the endpoints of the subintervals are ti. I ranges from 0 to n. So ti is I times delta t equals I times t over n. And the stochastic integral from 0 to t of the function xs with respect to the increments of the Brownian motion dws is defined as the limit as n tends to infinity, the sum from I equals to 1 to n, x at ti minus 1 times wti minus wti minus 1 quantity. So looking at the summand, the function x is evaluated at the left endpoint ti minus 1, and it gets multiplied by the increment of the Brownian motion in that time period. And to simplify the notation, we just write x of ti minus 1 as xi minus 1, and the increment of the Brownian motion as delta wi. This is not to be confused with the random walk, in which wi is only plus or minus 1. Here, delta wi can take continuous values. And we reiterate that the definition uses the left Riemann sum. Once again, this is to respect the non-anticipation assumption. Let's go over the diagram once again. So we have the time interval, partition it into n subintervals. At the I subinterval, we evaluate the function x at the left endpoint, multiply that by the increment of the Brownian motion over that subinterval, and do that for each subinterval and sum up all the contributions. And that's the definition of the Ito integral. And here we have a visualization of the definition. This is the function x, and here we have the Brownian motion. First, let's partition the time interval in the graph of x. Evaluate x at all the left endpoints. Notice that we don't even need the value of x at the final endpoint. And then we partition the time interval on the graph for the Brownian motion. And in each subinterval, we calculate the increments, delta w1, delta w2, and so on. And then we just calculate the weighted sum and take the limit. The integral from 0 to t, xs dws, is defined as the limit n goes to infinity of the sum I from 1 to n, xi minus 1 times delta wi. It all looks well and good, but we shall say something about the meaning of the limit. Yeah, so this is the intuitive definition. Okay, so we did not say much about what do we mean by taking the limit, right? So for example, in say the Riemann integral, yeah, where's did I close it? Yeah. So in a Riemann integral, you have a strict meaning for the limit, right? So here we also need to define limit in a somewhat more precise way. And this is what comes next. In stochastic calculus, we use the notion of mean square convergence. Okay, that is to say, we want the limit and the partial sum, okay, the proposed limit and the partial sum, to have zero variance as n tends to infinity. Okay, let's look at the precise definition for mean square convergence, because this is also quite important. Limit here. There are various notions of stochastic convergence, but here we're using the notion of mean square convergence, also known as L2 convergence. A sequence xi n of random variables is said to converge to another random variable xi in the mean square sense if for each n, xi n has finite second moment, also xi has finite second moment, and lastly, the most important condition, the expectation of xi n minus xi absolute value squared tends to 0. So here, because we're talking about the limit of an expectation, this is just the limit of a sequence of real numbers, which... Yes, so I was talking about after you take the expectation, right? This is just a sequence of real numbers, and you can talk about the limit of a sequence of real numbers tend to 0. So this is well understood. And indeed, this is a natural choice because this is a L2 distance. This is L2 distance. Actually, in advanced probability and stochastic process, you can actually construct eco-calculus, Ito's integral, using a Hilbert space construction. So this is all has to do with the geometry of the L2 space. So fundamentally speaking, Ito's calculus is a geometric object. This is a geometric object in the space of L2. Which we all understand from basic calculus. Borrowing the language of the L2 geometry, this is in fact a distance function. It says that the L2 distance between the sequence xi n and xi tends to 0. And we call xi the limit in the mean, or the mean square limit of xi n. And here are some common notations. We can write xi n converges to xi with an L2 on top of the arrow, or we can put a dot after each letter in the limit, L dot I dot M dot xi n equals to xi. This stands for the limit in the mean. So with this notion of mean square convergence, we can now write the definition of the Ito integral more precisely. We define yt, the stochastic integral, as the limit in the mean of the sum. And this is to say, the L2 distance between the random variable and the sum tends to 0 as n tends to infinity. As we can imagine, rigorous proofs of integrability is not a trivial matter. And by integrability, we of course mean that the random variable yt actually exists. And doing such proofs require measure-theoretic probability, which we would avoid almost entirely in this series. So yeah, that's the definition, the full definition of the Ito integral. I mean, it is workable. You don't need measure-theoretic probability to do it. You just need to know how to take variance, okay? Take expectation. That's enough for understanding Ito integral at this level, okay? We take the issue of existence and uniqueness as given and work with the rest. So basically, that's the philosophy of we take. Okay, this way you can still discuss convergence without being bogged down with measure theoretic probability. So here we can, because now it does not mention that in the paper. I don't think so. Did it say that? Okay, it does not seem to mention the L2 convergence here, but that's the precise meaning of the limit. Okay, so here, these two derivations we will actually do. Perhaps we should stop watching my own videos and just see some derivations myself. Yeah, it avoids the annoyance of square root 2. Yeah, you talk about the squared distance in L2. Okay, to summarize, let's do two examples. So as I said, Ito's rule, Ito's integral, just Ito integral is the choice alpha equals 0. That is to say, integral from 0 to t. Let's write g of t, dw of t is defined as the limit in the mean L dot I dot m dot as n tends to infinity. It stands for limit in the mean of the sum g of ti minus 1 times w of ti minus w of ti minus 1, right? As, oh, thank you very much. Sorry, I cannot pronounce your name, but thank you very much for your gift. As n tends to infinity, and the summation is from n to I from 1 to little n. So that's the Ito integral, defined this way. Okay, now you have also the Stochanovich integral, and you only need to modify one thing. Okay, so you only need to actually two things. First, you need a notation for the Stochanovich integral, and that's usually done by adding a little circle. Adding a little circle. So there's no universally agreed definition, universally agreed notation for Stochanovich integral. To emphasize this is Stochanovich integral, we use a little circle. It's almost like a composition symbol, okay, to stand for Stochanovich integral. And also some books like Gardner Stochastic Methods handbook, he uses a S. He uses a little S actually, S with a bracket, S with a bracket, 0 to t to represent Stochanovich integral, and then without the circle. That's another notation for Stochanovich integral, and of course the difference, as mentioned, is now g evaluated at the midpoint. G evaluated at midpoint, so that's tj minus 1 plus tj over 2. I'm claiming alpha equals 1 over... Oh, yeah. Yes. Yes, you can, everybody picks their favorite number between 0 and 1 and name the integral after themselves. Okay? Midpoint rule. You can get easy publication this way. I just invented a new stochastic integral. Left-hand point. Okay, so that's the Ito integral and Stratonovich integral. Let's see two examples to see why their rules are different. You got a whole career of papers. Let's go. Yeah. So, yeah, that's the two integrals. Let's see an example. Okay, so we want to see example. Integral from 0 to t, w of t, dw of t, okay, versus 0 to t, w of t, circle dw of t. Okay, so yeah, let's do the first example. The integral from w of t dw of t. Okay, so by definition, well, you're looking at the sum of, okay, we need this is A, and this is B. Okay, Ito. The sum I from 1 to n, right, and you have w of ti times w of ti minus w of ti minus 1. Okay, because writing this is extremely tiresome, I'm going to use the shortcut w of ti as wi. Okay, so this is just the sum of wi times wi minus wti. Or let's just write this as delta wi as well. Okay. wi minus wi minus 1, this is delta wi. Here. My God, what is my mouse doing today? I usually have no problem writing with a mouse, but today is awkward. Okay. This path is very irregular, but the change over that interval is called delta wi. wi times delta wi, I goes from 1 to n. So how do you sum this up? Well, let's consider a trick called telescoping sum. So this is our trick. Delta I plus 1 is wi plus 1 is wi plus delta. It's scared of the cat. The mouse is, oh wow, bro. Okay, so yeah, you made my day with that comment. wi squared, wi plus 1 squared is wi squared plus 2wi. It's just nothing but standard algebra, okay? Plus delta wi. Okay, so we want this term. You see, we want wi times delta wi, so you can isolate that, and you can write wi times delta wi as what? As 1/2 of wi plus 1 squared minus the oh, actually, I messed up, didn't I? I messed up. This is not a Ito integral. I'm using the right endpoint, for Christ's sake. Okay. I made a humongous mistake. This is not an Ito integral. Ti minus 1, okay, Ti minus 1. Holy crap. I made a big mistake. Okay, so this needs to be changed immediately. Okay, so here the algebra now changed. Minus 1, please. Okay. Okay, yeah, fix that ASAP. Minus 1 here, minus 1 here, minus 1 here. Oh, this is not minus 1. Yeah, minus 1 here. Oh, squared here. Minus delta Wi squared. Yes. Okay, great. Now it's good. Now let's substitute this into the summation. So you get a telescoping sum for the two terms, the first two terms. So you have I from 1 to n, wi squared minus wi minus 1 squared, minus half the sum of delta wi squared, I from 1 to n. So the first sum telescopes is just half of wn squared minus w0 squared. The first sum telescopes. Okay, so that's easy. But what about the next term? You have no algebraic way to simplify this. Right? The sum of delta wi squared is unclear algebraically. The first sum is the telescope sum. Okay, and oh, there's a square. What about this thing? Right, so well, if you take the limit, we have to consider what's the limit in the mean of this thing. But fortunately, we know delta wi is normal random variable. So there can be some work being done here. This second term, delta wi squared, is what? Delta wi is a normal random variable. Recall. Delta wi follows the distribution square root of delta t, normal 0, 1. And most importantly, these are IID random variables. Remember, delta wi is the increment over the I subinterval. So you have discretized your entire time interval from 0 to t into non-overlapping subintervals. So you see this is delta w1, delta w2, and so on. And of course, they're all independent. So this is great. And this is really awesome because we can say something about the sum of IID normal random variable squared. It follows the chi-square distribution. This is basic statistics, basic probability and statistics. Delta wi over the square root of delta t are IID normal 0, 1. Okay, so recall that from basic statistics, the sum of IID standard normal random variable is the chi-square. From probability, if you have z1 all the way to zn are IID normal 0, 1, then the sum of zi squared I from 1 to n follows the chi-square distribution with n degrees of freedom. So therefore, now you sum up delta wi squared over delta t. It follows the chi-square distribution with n degrees of freedom. Okay, so this is, of course, already proportional to the sum of delta wi squared. So you can calculate the mean and variance of this thing. So the mean of the sum of I from 1 to n. This is also a fact from the statistics. Basically, if S follows the chi-square n, then the mean of S is just the degrees of freedom n, and the variance of S. And the variance of S is what? The variance of S is 2n. Yeah. So that's a fact. No. Normal 0 is not a Gaussian distribution over the open interval. Normal 0, 1 is Gaussian distribution with 0 mean and standard deviation of 1. I mean, Gaussian distribution is always, it takes values always over the entire real line. Okay, there's no such thing as Gaussian distribution defined on a bounded set. Okay, so this is standard normal distribution. This notation represent the standard bell curve. Okay, this means the density of x is 1 over square root of 2 pi e to the minus x squared over 2. Okay, no worries. So we have the statistics for the chi-square distribution. So you can calculate the mean and variance of sum of delta wi squared. So the mean of this thing is delta t times n. Is delta t, multiply it to the right, times the mean of chi-square. So what is delta t times n? Well, delta t times n, that's the total time interval length, which is little t. Okay, awesome. No confusion now. And this is a constant for all t. The mean does not depend on t. Okay, what about the variance? The variance of the same sum, the leftover term, second order term, 1 from n, delta wi squared. Okay, that's delta t squared, because remember, if you multiply a random variable by a constant, in this case multiplied by delta t, the variance gets multiplied by that constant squared. So it's delta t squared times 2n. But what's that? Well, we already know delta t times n is the total length, so t, so you get 2t times delta t. But as n tends to infinity, or delta t tends to 0, same thing. As delta t tends to 0, this variance tends to 0. You see, here you have a term whose variance tends to 0, but the mean is a constant t. Therefore, in the L2 sense, it converges to this fixed number t. So therefore, we get our limit. The Ito sum in the L2 sense tends to, here, the first term, the telescoping sum, you don't need to do anything about that, and minus half t. So let's write the conclusion. Therefore, the Ito integral 0 to t, w of t dw of t is half, okay, so you get half wn squared. Okay? Wn squared is what? Wn squared, that's just the value of w at the final time, at the last endpoint, which is just w of t. So wn, this is just w of t squared, and then minus half t. So we have calculated our first stochastic integral. Okay. So this is interesting because of the analysis of the final term, the leftover term. You see why this is interesting? Because if you pretend w of t to be a regular function, just a normal function in calculus, what you should get is the integral from t, w of t, dwt equals half wt squared without the leftover term. Right? So remember from just the chain rule, right? The chain rule or the U substitution in calculus. If you integrate U sub rule from calculus, the integral, say, of a function g of t, and then g prime of t, dt, which you can write this as dg of t. Right? The U sub's rule tells us this is half g of t squared minus half of g of 0 squared. And if g of 0 is 0, this term cancels. So here we have this extra term. And this extra term is the result of the limit of the sum of delta I squared. So that is to say, the quadratic variation of the Brownian motion does not tend to 0. This term is called a quadratic variation. The quadratic variation of the Brownian motion do not tend to 0. And that's different from regular calculus. In regular calculus, the quadratic variation of a smooth function always tend to 0. Let's look at, without going into the detailed proofs, because I already also made videos on them, to emphasize the origin of stochastic calculus. Here, in this video,
Hello, this is the second episode.
In the second episode, we revisited standard calculus. Here, you see, if we integrate x dx and we use a discrete sum, right, to estimate the integral, the error would be the total area of these little triangles. And these little triangles vanishes as the partition gets finer and finer. So here, this is the total error. The total error is the sum of the area of all little triangles. Right? See, the little triangles have length, leg delta x. So each triangle has a length of half delta x, and you half delta x squared, and then you just sum them up. It is proportional to delta x. So of course, as delta x tends to 0, the error tends to 0. Here we see a non-vanishing quadratic variation. Let's put them side by side to make this extra clear. So this is the deterministic quadratic variation, sum of delta. Come on. Yeah, you see, sum of half delta x squared. That's the deterministic quadratic variation. But here we have half delta w squared. This do not tend to 0. And because of the non-vanishing quadratic variation of the Brownian motion, regular calculus, the U sub rule, fails. So that's the crucial reason why Ito calculus need a new calculus. So from this simple example, okay. So when we have the and once again, quadratic variation don't vanish is because of the delta t. See, it's because of the square root of delta t, and this causes the Brownian motion to be extremely irregular. This scaling law causes the Brownian motion to be extremely irregular. It's nowhere differentiable, because you can heuristically justify this by considering the change of delta wi over the square root over delta t. Okay, that would be the discrete derivative, right? So this would be what? This would be 1 over square root of delta t times the normal distribution. But the thing is, as delta t tends to 0, this blows up as delta t tends to 0. Right? Tough to learn math, but these streams make it manageable. Recommend same book he's using on stream. Yes, yes. So yeah, I do not promise an easy path because that would be lying, in my opinion. But I do try to make things manageable um, for a general audience. Okay, if you want to learn this, there's a way to do this, but it requires a lot of repetition and not repetition in a mechanical way, but try to internalize intuition. So I'm trying to keep the introduction as intuitive as possible. So the Brownian motion has this non-vanishing quadratic variation precisely because of its non-smooth path. And for smooth path, okay, for smooth path, then you can ignore the quadratic variation. So I made a video not too long ago called "Is dx squared ignorable?" Is dx squared
When
ignorable?
the change in sales dq is small, however,
we only considered deterministic functions. Here we only consider deterministic functions. So the same picture is here. You can prove the quadratic variation for two smooth functions vanishes. Okay, so here you have two smooth functions, df and dg. F and G. So f and g are differentiable functions, so you can apply linear approximation to it. That is the tangent line approximation. And it is rigorously justified by the mean value theorem. You can look at the proof here, but this is not our main point. The main point is already in this picture. Here, where's the picture? Where is, yeah, this picture. For deterministic smooth function, actually it has nothing to do with deterministicness. It's just for smooth functions. For differentiable functions, the quadratic variation tends to 0 because of this picture. However, if the path gets sufficiently rough, even for deterministic function, you can have non-zero quadratic variation. And here I gave an example. This is the classic nowhere smooth function, the Weierstrass function, but it is kind of complicated because it involves a cosine, a transcendental function. So here we have a simpler example. It's called the Takagi-Landsberg curve. In his opinion, generations fundamental in stochastic with probably 4 stochastics on stochastic, a completely deterministic counterexample known as Takagi-Landsberg curves. And we shall show that for some of its members, its higher order differentials cannot be ignored, just like in the Brownian motion. And here's the idea. Okay. So this is called a special case called the blancmange curve, because it kind of looks like a dessert. So it is also nowhere smooth. Not Blancmange curve, but another specific member of the Takagi-Landsberg curve family. And you can construct it this way. And here's the idea of the construction of the Takagi-Landsberg curve. We start with a triangle wave function. The value of the function is defined as the distance from x to its nearest integer. And now we're just going to make higher and higher frequencies of the triangle wave, with its frequency doubled at each time. So if we call the original triangle wave f of x, this is f of 2x, that is double the frequency. Doubling the frequency again, we get f of 4x. Doubling the frequency again, we get f of 8x, and so on. And now we have the formula for the TL curves. So explain. The function phi is a triangle wave function. Okay, it has a non-differentiable point at these corners, obviously. And the 2 to the n factor makes the frequency doubles. Okay, makes the frequency double. So phi of 2x is doubling the frequency. Phi of the 4x is quadrupling the frequency, and so on. So now we want to make superpositions of these waves. This way, you have more and more non-smooth points on the t-axis, because as we can see, doubling the frequency add more non-smoothness, and then you have more non-smoothness. So that's the idea. And here on the at the beginning you have a to the n. That's an adjustment factor, because if you simply add them together, then the sum would not converge. It will blow up. So adding this a to the n is like a geometric series. Right? You compress it by this factor a to the n. Because the function phi is bounded, right, it is between 0 and 1/2. Multiplying this by a to the n ensures convergence. So that's the role of a to the n. And a is between 0 and 1. That's a parameter. And it turns out that you can tweak the values of a to make sure the final curve to be smooth or rough. Okay, let's take a look at the visualization here. Phi of x is the triangle wave. The idea is we can make higher and higher frequencies of the triangle wave and add them together so that the real line is filled with non-smooth points. And let's see what the sum looks like in Desmos. It's highly interesting. In Desmos, we're only adding the first. Actually, you know what? Let's go to Desmos, and I'll show you the visualization there. This way, I can drag and do the animation. Free account. I mean, already sign up, log in. I think it's this one. What's going on? Okay, let me retry. Okay, so I just signed in, and yeah, this is the curve. So I only added 10 terms because obviously you cannot add infinitely many terms. But already the intuition is quite clear. So this is a equals 0. When a equals 0, you just have the first initial triangle wave. And let's see what happens when a increases. I play this very slowly. Yeah. Increase a. As a tends to 1, the sum blows up. As a tends to 1, if it's the infinite sum, then the sum will obviously blow up. So it gets rougher and rougher as you increase a. As I said it in the video, it's like baking a cake, seeing a cake rise in the oven. Okay, so that's pretty cool. So this is a completely deterministic function, and it's a fractal curve. So for details that isn't super important for the rest of our discussion is that if you pick a to be 1 over square root of 2, you can show that the quadratic variation do not vanish. The quadratic variation is non-trivial. So regardless how fine you partition the domain, the quadratic variation do not vanish because it has a lower bound of 1/4. For all n, Qn is greater or equal to 1/4, and therefore the limit is non-zero. So even for deterministic curves, you have this non-vanishing quadratic variation behavior. Okay, it's not because Brownian motion is random, therefore you need a new calculus. That's not the explanation. It's because Brownian motion is rough, and the roughness comes from the square root of t scaling factor. Because of the variance is linear in time. That's the fundamental reason. And in fact, this spawned an entire new field of mathematics called the rough path theory. It's quite new, called rough path theory. So intuitively, you can think about that's the natural next step of Brownian motion. So Brownian motion breaks calculus, right? So we wanted to say how else can calculus break, right? How else if you make the path rough, what sort of new calculus do you get? You can think of this way. It's introduced in the 90s. Okay. In stochastic analysis, a rough path, and once again, the path itself can be deterministic. It's just that the most common example of a rough path arises from stochastic calculus and also in fractal geometry as well. Rough path is a generalization of the classic notion of a smooth path. It extends calculus and differential equation theory to handle irregular signals, paths that are too rough for traditional analysis, such as a Wiener process. This makes it possible to define and solve control differential equation of this form. So now dxt can be, for example, the driving path, the Brownian path. This is very rough, and you can define roughness in a general way. Okay, of course, this is very much the frontier of mathematical research. So it's a very new. I mean, roughly speaking, technically, if a math subject is less than 3 decades, it is new. Right, think about it. One typically only learns measure theory, which is introduced in the beginning of the 20th century, late 19th century, very late 19th century, when you enter grad school or late undergraduate. So you see, math is a little bit different compared to many other subjects. So even math 100 years ago is basically graduate mathematics, and this is of course very advanced research level math. Okay, so yeah, things are continuous paths takes paths in the Banach space, need not to be differentiable or have bounded variation. Very interesting field, but I don't think I can do a live on this anytime soon. Okay, so that's the natural next step, right? Once we realize you have this sort of inspired by Brownian motion, right? Non-smooth paths give rise to new calculus, not randomness. Okay, I think I already kind of sound like a broken record at this point. I should stop. Okay, so that's our first example. Explain why stochastic calculus is needed. They don't have to be bounded variation. Yeah, called rough path theory. Very interesting, but very formidable as well. So good luck. There are a few tutorial style introduction to rough path theory, but still. Okay, let's look at the second example. The second example is actually much easier, provided we use the fact that, okay, so it's not proved because that's a little bit technical. The idea is W at the midpoint, because the Stratonovich sum calls for the midpoint approximation, Ti plus Ti minus 1 over 2. So W at the midpoint is roughly the average. This is intuitive because after all, W is a continuous function. So for sufficiently small time interval, the value at the midpoint should roughly be the value at between the endpoints. The value at the endpoint should roughly be the same as at the endpoint. Okay, so and then plus little o of delta t. This nice thing is, if you sum up the little o of delta t, it has nothing to contribute in the final integration. Remember earlier, like in the triangle example, triangle function. Here, in the triangle function, the error term, actually each individual error term is of higher order of delta x. It's delta x squared. That's a higher order term. But it does not need to be square, right? If the exponent is bigger than 1, is strictly bigger than 1, then you would guarantee error tends to 0 as delta x tends to 0. It doesn't need to be strictly quadratic. It just needs to be higher order than delta x. And this is what the approximation says. The approximation of the midpoint is roughly the average of the function of the endpoints plus a negligible term, higher order of delta t. So this contributes nothing to the integration. So therefore we can write the Stochanovich sum, W of the midpoint, times the increment of the Brownian motion Okay, draw the diagram again. This is the interval ti minus 1. This is ti. This is the sampling point. Let's actually just call it ti bar. Why not? Because that's the average. I from 1 to n. So you can write this as approximately the sum of half of w of ti plus w of ti. This is not minus 1. What am I doing? W of ti minus 1. Lots of subscripts and stuff, so easy to make mistake. Okay, and then times the difference. W of ti minus W of ti minus 1. So this is the difference of squares. And this sum automatically telescopes, so which makes things a lot easier. There's no quadratic variation term to worry about here. Okay, so this gives us W. You see this is a telescoping sum, so this gives you W of n squared, W of Tn squared, so this final time, so W of T squared minus half W of 0 squared. Well, that was easy, exactly. Yeah, because of this approximation. Right, so as n tends to infinity. As n tends to infinity, the limit is not affected. So basically, the Stochanovich integral, it behaves just like regular calculus. 0 to t, W of t, circle dW of t is half of W of t squared, exactly just like regular calculus, you see? This works just like the U substitution rule. So that's cool. You don't need extra calculus, new rules of calculus to handle Stochanovich integrals. So that's basically what the Hyam's paper is talking about here. Yeah, we did the calculation here, and there's numerical simulation. Okay, so let's just briefly skim through this. We saw this. Okay, so this is the approximation for the midpoint. The error is negligible. Okay, and this is some details in the numerical simulation. So this here it says this highlights a significant difference between deterministic and stochastic integration in defining stochastic integral as a limiting case of Riemann sum. We must be precise about how the sum is formed. The left-hand sum gives rise to what is known as the Ito integral, whereas the midpoint sum produces the Stochanovich integral. Okay, so here you have the analytic formula, right? Analytic formula. So we have this is the Ito integral result, same algebra we did earlier, and for the Stochanovich integral, you see the limiting case of this thing, the error term vanishes, and you just end up having a regular calculus rule. Okay, the regular U substitution rule still holds, and this is quite in general actually. Stochanovich calculus do not require extra rule of calculus. The chain rule, product rule, and stuff still works here. Okay. So there's that. Okay, so now it is time to introduce stochastic differential equation. So for stochastic differential equation, we can finally introduce stochastic differential equation because, well, I don't think this what we did was waste of time. In fact, I should consider them to be pretty fundamental. You see, you can only discuss differential equation, ordinary differential equation, if you understand derivatives and integral, right? So first we have to clear things up, like what do stochastic calculus mean, right? And then we can talk about stochastic differential equation. Okay, so finally, stochastic differential equation. Here I'm going to use my own notes here, okay, before we come back to numerical simulation. Perhaps we don't have time for numerical simulation today because it's already 11:30. I have half an hour. Let's talk about stochastic differential equation and their examples. Okay, let's go. So first we have just the ODE, right? Start from the ODE. ODE, let's just do the scalar case, okay? F from R to R. Now, yes, now we can really start. You see, yeah, now we can really start. So you have x dot of t equals f of xt. Okay, and x of t, I mean, this is a differential equation, right? That's the ODE. And typically, ODE also come with an initial condition as well. ODE plus initial condition, IC, right? IC says x of 0 equals x naught. Okay, and these two together, the initial value problem, now this is well known in regular calculus, together they're equivalent to an integral equation. Together they are equivalent to an integral equation, basically that says this: x of t minus x naught. Yeah, I was thinking, okay, basically we're done. No, this is the start. Xt minus x naught is integral from 0 to t, f of x of s ds. Of course, this is not really saying much, right? Because after all, on the right-hand side, it involves the unknown function. It's not like you can evaluate x of t, but it is an equivalent formulation. Okay, it's an equivalent formulation. So the ODE can be written in several ways. So you can write it as, say, x dx equals f of x times dt. Okay, ODE has all these different notations. So ODE, okay, the classic notation is x dot of t equals f of xt. Right? You can also write it in the differential notation. Perhaps this is more useful for applied scientists because we like to think of dt being a very small interval of time and then just formulate the increments directly, right? Instead of dividing by t, dividing by increment of time and pass to the limit. Right? So these are all equivalent form of the ODE, and initial condition, adding the initial condition gives you an initial value problem, and the initial value problem is equivalent to the integral equation. I hope this is clear. Right, this is an integral equation. Okay, the integral equation, even though on the surface it doesn't seem very useful, right? It's not like you can calculate xt explicitly, but it is actually quite useful for studying first of all, the existence and uniqueness of the solution, as well as constructing approximation. There is a method that comes with this formulation. Okay, so basically, these are all useful formulations. Initial value problem is equivalent to an integral equation, i.e. Okay, so what is the stochastic side of the story? Well, for the stochastic side of the story, you can do the following. Actually, you know what? I'm going to slightly generalizing a little bit because f can still be time dependent. F does not have to be from R to R. Okay, it can be time dependent as well. The law for governing t can be time dependent as well. So let's put R times R. That will be more natural, actually. Quite often you have f as a function of x only. In that case, we call it an autonomous system. That is to say, f doesn't change over time. If that's the case, if that's not the case, it's non-autonomous, you add a little t in there as an argument of f. So this will be the most general ODE for practical purposes. Of course, they're not, ODEs aren't always like this, but this is general enough. Okay, so here, what would be the stochastic analog of this? Actually, before we talk about stochastic analog, let's do a concrete example. The exponential growth. Example, exponential growth. So x dot, I think everyone's seen exponential growth, so I'll stop motivating. So x dot is a times x of t. So this is the same as dx equals a x dt. So it says that the increment of x over a short time interval is proportional to the value of x, like a compound interest model, continuous time compound interest model. Okay, so this is equivalent to x of t minus x of 0 equals the integral from 0 to t ax of s ds. Right, so what is the stochastic side of the story? Let's say you want to add noise to the system. Analog differential equation. So the stochastic differential equation driven by the Brownian motion looks like the following. Okay, so it is written this way. So let's start with the middle notation. Okay, dx, big X, so random process usually denoted as a big letter unless you're a physicist. Okay, so dx equals dx of t equals which we call mu. Okay, mu of x of t nt dt. Well, this is the deterministic component. Because mu is a deterministic function. If you know the current value of xt, you can evaluate the mu term and then multiply bt dt. So these are all deterministic. Deterministic component plus a random component. A random component is written as sigma. Sigma is called the volatility parameter. By the way, mu is called drift because it governs the deterministic growth or decay, right? So that's the drift. Sigma is called volatility. These terms came from finance. X of t and t. So this tells us the volatility, but you need a randomness to it, right? This is still a deterministic function, so this gets multiplied by dw of t. Okay. So the Brownian motion is what is added to the OD to make it stochastic. Exactly. Exactly. So that's exactly the random component. So it's the ODE with an extra term, which is a random noise. It came from Langevin's study of Brownian motion. Okay, so this is a bit of a crossover with the stochastic process for physics theory. Okay, let me just go back to the notes by Professor Matt Scott. So this is motivated from physics. So it started with the Langevin study of Brownian motion, which is why Langevin is on the thumbnail. This guy, Langevin. So Brownian motion a la Langevin, according to Langevin. Okay, so Brownian motion in physics is this, has this picture. So big circle is a pollen grain, and little particles are water molecules or just solvent molecules like oil or whatever. Okay, so they collide. Okay, so the picture is they collide with the Brownian particle, so it gives this random kick. It's considered random because there are so many solvent particles surrounding the Brownian particle that modeling the precise nature of the collision force is impractical. Okay, and the Brownian particle submerged in the fluid can be considered to experience two forces. Okay, so if one source is the random kicking force, which we group them into one random term, and another force is the viscous drag. So the surrounding particles kick the Brownian particle, or the surrounding particle kick the pollen grain, so that it can obtain a momentum, right? It got kicked. But immediately the surrounding medium, due to viscosity, slows it down. So that's the restoring mechanism. And together they form a differential equation, the Newton's law. Okay, so basically here, this is Einstein's a different approach, which we also covered here. In the Brownian motion, Brownian motion model, according to Langevin, he formulated a differential equation. This one, this is Newton's law. Ma on the left-hand side. On the right, you have the viscous drag force minus gamma dx over dt. That's the Stokes law. This is a deterministic term, plus the random fluctuation term. Okay, and of course you can write dx dt as the velocity, so that the differential equation becomes first order, and that's here. And this is called the Øksendal process. The velocity of Brownian motion is called the Øksendal process. U is velocity, so you have dm over dt, okay, minus gamma u plus the random force. This is Langevin's equation. Original Langevin's equation, but just written in terms of the velocity. Okay. So, but the problem mathematically, this is undefined. Remember earlier that Brownian motion is nowhere differentiable, and as a result, the solution turns out to be actually also nowhere differentiable. So writing d over dt is troublesome. So instead, we use the differential notation. Nevertheless, physicists also often write x dot, still even to this day. So this is written as the following. So imagine if we divide by dt on both sides. Okay, if we divide by dt on both sides, this way you get x dot of t equals mu of x of t times t. So this is like the drag force in the Langevin's equation, and then plus sigma x of t and t, and then times dw dt. But the thing is, you see, dw dt is undefined, right? We saw that earlier. Brownian motion is not differentiable. So instead, physicists talk about the white noise. You can think of dw over dt as so-called white noise. So the white noise, of course, is not a stochastic process in the traditional sense. After all, dw dt is not even a function. It can only be interpreted in some distributional sense, like a direct delta, which is also very commonly used in physics. So this is so physicists use eta. Now, typically denote this by eta. Eta, that's the white noise. Eta of t, that's the white noise. You can think of it as the symbolic derivative of the Wiener process or Brownian motion. Mathematically speaking, delta of t is not a classically defined sample path, but it can be seen as generalized function. There are ways to rigorize this, although physicists don't usually care about the rigorous definition of white noise anyway. So these two are equivalent. Okay, we will mostly be using the second form. Okay, but still, this is not the end of the resolution, right? So even though if you can write the increment instead of the derivative, this way you avoid the issue of differentiability, right? Because now you can look at this equation and simply say, over a small time interval with length dt, the increment of xt is given by this. So that's good. This avoids the differentiability issue, but you still have to convert this into integral. After all, it's not the differential that you care about, it's the cumulative effect, right? So let's integrate that. This is equivalent to an integral equation x of t minus x of 0 if you integrate over both sides from 0 to t, okay, ds. So this way you get an integral equation. Integral equation for the stochastic process, xt. And what's the result? Well, the first term is from 0 to t, mu of x of s and s ds. That's the first term. And the second term is 0 to t, sigma of x of s, s, and then dw of s. The first term is unambiguous. This is just a Riemann integral. You see, this is because of ds. This is just a Riemann integral. Even though xs may be random, xs is still continuous. So if mu is well behaved, if mu is continuous, then the first term is just integrating a continuous function. There's no problem with that. Riemann integrals are well suited to handle continuous function. So there's no issue. There's no mathematical ambiguity for the first term, even when x of t is random. You can think of x of s as a sample path. Once that is observed, then the first term is just a continuous function. So there's no mathematical issue handling the first one. However, we've seen earlier that the second term is ambiguous. This is a stochastic integral, which means you have to choose an interpretation. Mu doesn't have to be constant. Mu does not have to be constant. In fact, most cases mu aren't. Here, for example, in the exponential growth, mu is the linear function. Mu equals a times x. It doesn't have to be constant. Okay, but nevertheless, mu is a deterministic function. If you know x and you know t, then mu of x and t is decided. There's no randomness to it anymore. Okay, so the second term is stochastic, which means you have to choose a meaning. This is ambiguous. Is this Ito integral? Or is this Stochanovich integral? Or even something else? So there's a modeling choice to be involved here. Okay, and if the integral is interpreted in the Ito sense, then we call it Ito SDE. Or if it's in the Stochanovich sense, it's called the Stochanovich SDE. Okay, so there's that. That's the stochastic differential equation, and the first example is the GBM, the geometric Brownian motion. Geometric Brownian motion is one of the few examples of SDE that has an analytic solution. Geometric Brownian motion. Although today we won't solve it, I mean it's in the videos anyway, because it requires Ito's lemma. Okay, solving geometric Brownian motion analytically requires Ito's lemma, but stating the differential equation do not. So here you can think of, say, dx over big X. So think of X as the price, the market price of some asset. Dx over X, that is dx of t, okay? Dx of t over dt, that's the increment in X over X. That's what? Increment over X of t, that's the interest rate. This is the interest rate over a small time interval t to dt. This is interest rate. Interest rate for asset big X of t over the interval t to t plus dt. Okay, so much like modeling Brownian motion, you can think of the interest rate being mostly fixed but subject to a random disturbance. So you can assume the interest rate being a constant and then plus random disturbance. Random disturbance being modeled as white noise. Isn't Brownian motion is just pressure in the continuous? What do you mean by pressure? Brownian motion, mathematically speaking, is the limit of random walk in the continuous sense, explained in the video series. Here. Brownian motion is interpreted as the limit of random walk. Pressure is no, it has nothing to do with pressure. Pressure is not a stochastic phenomenon. Okay. You mean pressure from in thermodynamics? That's not a stochastic phenomenon. Okay. You can explain pressure using deterministic Newton's law. Okay. So plus random disturbance, which is modeled as white noise. So what this says is dx of t over x of t is constant, say mu, or sometimes you write r for the interest rate r, and then plus what? Plus sigma, which is the volatility parameter, times eta of t, random noise. So this is equivalent to dx of t equals mu, oh sorry, my bad. The constant should also be proportional to dt, right? Because after all, this is the interest rate over a tiny interval. The interest rate in a tiny interval should also be tiny. Okay, so mu of x of t times dt. These SDs are now hot cake in thermodynamic computing. Yeah, SD is really everywhere. And then plus here, what else? Oh, actually, I think I made a mistake here. I wanted to say is the random noise is not modeled by white noise, but rather Wiener process. Random disturbance is modeled as Brownian motion. Okay, my bad. Because we're using not time derivative, right? This is just the increment in the interest rate. Sorry, this is just interest rate. Interest rate is modeled as constant plus random disturbance, which is modeled as Wiener process or Brownian motion. This is dWt. My bad. I got confused there. So now it's good. Sigma times big X of t dWt. And this is what we call the geometric Brownian motion. So intuitively, how do geometric Brownian motion behave? Well, without the volatility, if volatility sigma is 0, it should just be an exponential growth. And now because of the introduction of sigma, it becomes like this. It fluctuates around that. Actually, it's also it's a diagram that's given in the paper. Okay, I'm terrible with drawing random paths, or terrible with drawing in general. But this is basically the model here. The geometric Brownian motions have sample paths that look like this. Geometric Brownian motion is absolutely brutal. The volatility is insane. Okay, for moderate sigma, the long-term variation can be very crazy. So even though the mean is exponential growth, the spread is insane. This is the geometric Brownian motion. And the solution of the geometric Brownian motion here, I think it has a formula, 4.6. Yes. Yeah. So this is a geometric Brownian motion we just derived. Here, you see the first term. It's the same as what we have here. It says lambda x of t. We write mu of x of t. Where's going on? Yeah, mu of x of t. Oh, yeah. Here you use mu, but we use sigma. Different parameter, volatility parameter, x of t dwt with initial condition. When these two are real constant, this SDE arises, for example, as an asset price model in financial mathematics. This is one of the fundamental assumptions behind the Black-Scholes model, geometric Brownian motion. Indeed, that's the well-known Black-Scholes PDE can be derived from it. Yeah. So I don't know, guys. Next week, Black-Scholes or diffusion model, up to you. Okay, and the exact solution can be derived using Ito's lemma, which we derived in the video. Yeah, so how mean returns lie, Ito's lemma, GBM, volatility drag. So we use the Ito's lemma to solve the GBM here. So we already have the foundation to do Black-Scholes. And this is the solution, analytic solution. So that's an example of stochastic differential equation. GBM is perhaps the most well-known stochastic differential equation, but there's a lot of other interesting models too. Okay, here let me just give you another example, which is nonlinear. Okay, this is a linear, because xt appears linear in a linear term. Okay, so you can use it for population dynamics as well. Okay, questions. So you have in signal processing you have to account for random errors. So any sort of electronics these days is going to be using some sort of stochastic. Yeah, there's something called the Johnson's noise actually. So if you go to Professor Scott's text, which is link in the stochastic process for physicists video. You know, I'm a sneaky bastard, am I? I'm using these book references to farm views. So if you want the node, you have to go to the link, and then I get farm view. How sneaky am I? Anyway, so where's the Johnson's noise? Yeah, indeed, electric circuits is another situation where Brownian motion-like behavior arises, called the Johnson-Nyquist circuit. Okay, and you see you have the differential equation for the charge dq dt. So this is a classic RC circuit. Classic RC is discharging of the capacitor, and now have a random disturbance to it, eta t, that's the white noise. So this is a stochastic differential equation, and the resulting noise is called the Johnson noise. So it's just a nice paradox because it's the same differential equation as in the Brownian motion, but just different physical interpretation. Okay, pretty cool stuff. Go check this out if you're interested. Okay, so we're getting towards the end of our stream. So I'm just going to give another example. So basically what we established is that for any ODE, you can add a noise term to it. Another example from population dynamics. We all know the logistic model, right? From the classic logistic model, logistic growth, which is actually quite depressing if you think about it. So the Malthus model is very depressing. That's the exponential growth model. X dot equals kx, right? Malthus says, okay, because of this is how population grow in time, it's exponential growth, but resources don't grow at the same rate. So eventually you're going to have mass starvation and war between nations, and you end up getting this cyclic evolution of overpopulation, and then people die, and people die due to famine and war and stuff. A very depressing guy. So in response to Malthus, somebody says, well, wait a minute, it doesn't actually work that way, because you can, let's put R here, okay, let's put R, because you never have exponential growth in the long term because of the environment, the resources, whatever, has a finite carrying capacity. And that finite carrying capacity is called big K. So big K minus X. Okay. As a result, this is a logistic model which solves the overpopulation prediction. Right? Because theoretically, it is capped under big K. So you end up getting this S-shaped curve, the sigmoid curve, known as the logistic curve. But it's also depressing in its own way, because to get sustainable development, it says the death rate here, this is RKX, that's the growth rate, minus RX squared, that's the death rate. So death will eventually outpace growth. Quadratic function eventually beat linear function. So it means the suffering in the population will eventually exceed life, happiness. Also a very grim picture. You know, economists are the worst kind of people. Economists, sorry, my bad. This is a joke, okay? In case somebody get pissed off and unsubscribe from the channel. Economics has a nickname called the dismal science. So it's prediction, and they tend to be very pessimistic about human nature when it comes to fundamental assumptions. Okay. Anyway, coming back to the mathematics, this is the classic logistic growth. You can add a random term to it. Okay. So what's the idea of a logistic growth? The logistic growth says x dot, or let's put it this way, in a differential form, dx over x, that's the rate, right? Rate of growth, just like how we analyze the rate of growth, interest rate, infinitesimal time. Right. So dx over x is rk, the constant, minus rx. So the logistic growth model says the growth rate, oh, actually you need a dt at the end. So it says the growth rate, much like the interest rate. This is the growth percentage rate, not rate over time. Okay, growth percentage rate is a decreasing function linearly in the population size. It's decreasing linearly in x. And then you can add random term to it. Okay, you can add random disturbance term to it. So now let's do the stochastic version. So the SDE model should have an obvious form. So you have rk minus rx, okay, times dt, and then plus sigma, okay, sigma is a constant, times dwt, noise. So therefore, this way you get an SDE. Right, for SDE, let's use big X. So dx is r big X times k minus big X dt, and then plus sigma big X dwt. Okay, of course here X should all have a bracket little t behind it. I mean, I'm just using this to save some writing. And this is a population dynamic model. And actually it also have an analytic solution. It also have an analytic solution. To do that, you would need Ito's lemma available, okay? So that's about wrapping things up. Okay, thank you very much, guys, for joining the stream. And SDE is very much a great topic. We wish to we'll do a recurring series, episodes, live stream, or whatever on it. Okay, and we will condense some of our discussion into shorter form videos to add to the Stochastic Calculus for Beginners series. Okay, so that's it for today. Thank you very much for joining the stream. Bye.